Okay. Hello, everyone. Welcome, and thank you very much for coming to this tutorial on the real-world processing in memory architectures that we organized, the Safari Research Group, Professor Mutlu and I organized today. We are really lucky to have this opportunity. As you may know, it's the second edition of this real-world processing in memory tutorial. We delivered it first at the HPCA 2023, a month ago exactly in Montreal, and it was a really very nice experience. Today we have novelties. It's not going to be exactly the same, even though there will be for sure some common lectures, but we are lucky to have several invited speakers. As you see, Professor Sasha Fedorova from the University of British Columbia, and then we'll have Kwong and Eddie Park from SK Hynix, who will introduce the SK Hynix AIM processing in memory architecture. I'm going to very briefly show you the agenda of this tutorial, and after that we will go with the next lecture. Or with the first lecture. Okay, so I hope you can see it well. This is the agenda, but you can also find it in our website. Over the course. Yeah, give me 1 second because it seems that I'm not sharing the right thing. So I hope it should be fine now. Yeah, this is the agenda of today's tutorial. As you see, we are going to start with the talk by Professor Mutlu on memory-centric computing, an introduction to processing in memory. He's going to explain what are the reasons why we need to move to more memory-centric computing systems and what those reasons justify the introduction of processing in memory architectures in our computing systems. He will also give a very first view of this taxonomy of processing in memory that distinguishes between processing near memory and processing using memory systems. We are going to talk about both types of systems today. After that, we will have the coffee break, as you see, and next I will talk about processing near memory systems. I'm going to give you an overview of the current processing near memory systems in the real world, starting with the HBM-PIM architecture, which is the first commercially available processing in memory architecture, but we will also talk about prototypes from Samsung, from SK Hynix, or from Alibaba. After the lunch, we will have Professor Fedorova talking about her experiences, the experiences of her group with processing in memory as well. They have also a very interesting experience with the HBM-PIM architecture. And then we will deliver a lecture on processing using memory. We are going to talk about the recent works on processing using memory, with the participation as well of Ataberk Olgun, who is a PhD student in our research group, in the Safari Research Group. He has developed an end-to-end framework to evaluate and test processing using memory ideas. I think it's a pretty interesting work as well. After the second coffee break, short lecture about how to enable processing in memory. I will also give you an overview of our experience with some important real-world workloads that we have implemented for the HBM-PIM architecture. And next, we will have SK Hynix folks, Dr. Kwong and Eddie Park, who will introduce the AIM architecture. I think this is really interesting work, and it also, I mean, it's going to be perfect complement for the rest. I mean, to the rest of the tutorial. And finally, in just the last few minutes, I will give you a short introduction to the optional hands-on lab that we have prepared for the HBM-PIM architecture. This time we don't have time because the tutorial is a little bit shorter than it was in at HPCA. But as I will explain you, and actually you can already check the handout in the website of the tutorial. As I will explain you, you can access a real server from HBM that is reserved for us. You can download the materials and have your own experience. So I hope it will be a nice experience. I will be also online to help you. And I think it will be available for us until 6 a.m. or something like that. So now, if you are ready, it's going to be my pleasure to introduce Professor Mutlu. Onur, are you ready?
Hello, Juan. Yes.
Very
I
good.
can share my screen, I think. Does all look good?
1 second.
Sure, I'll wait until you tell me. That's good.
Okay, yes, I can see you. I think we are ready to go.
Okay, great.
Let me introduce you just for a second, even though
Okay.
Everyone knows you here. Professor Mutlu, he's a full professor at the ETH Zurich. Before that, he was a professor at Carnegie Mellon University. He's with ETH since 2015 or 2016, and he leads the Safari Research Group. I'm a proud member of this Safari Research Group. As you may know, we do research in computer architecture in many different things with a special focus on memory systems, storage, processing in memory. We also work with applications like bioinformatics especially, and many more things. Now, Onur, if you're ready, please go ahead and start.
Yeah, sounds good. Thanks a lot, Juan, and thanks everyone for coming for the second edition of our tutorial. I wanted to be there in person, but I couldn't make it this time, unfortunately. So, but hopefully you can still ask questions as if I were there. So I'm happy to take questions anytime. Just I would coordinate with Juan on site over there. So I'm going to give you an overall view of memory-centric computing from our perspective. This is an area that's quite exciting, as you may see from the conferences, as well as industry today. And I'll give a motivation, as Juan mentioned. So let's get started and an overview of the field. So today, it's very clear that computing is bottlenecked by data. And data is really key for major applications. And we see it in many domains today. Clearly, machine learning is an example, genomics is an example. But all important workloads are data intensive, and they require rapid and efficient processing of large amounts of data. And on top of this, data is increasing. We can generate much more data than we can process in many, many fields. And also, we want to do more sophisticated, increasingly sophisticated things on the data. And this is an example. This is neural networks. Clearly, they've been growing very quickly. This picture I borrow from Sean Lee, who's the chief architect of the Cerebras company, who's essentially trying to build wafer scale chips to accelerate machine learning. And they basically show that compute requirements are growing exponentially, and at the same time, memory requirements are growing exponentially. So we need to solve not just the compute problem, but especially the memory problem. And this is true for many, many applications. Many, many applications are growing in terms of data sets, as well as the things that we do on the data. So data is a huge performance energy bottleneck today. I'll quantify these statements later on. And even on the mobile end, there are quite a few applications that we're exercising right now, actually. We're using Zoom, we're using YouTube, we're using web pages, and there's some machine learning going on in the background. So all of these applications are being exercised right now. And these are also quite a bottleneck by data in the end. I'm going to talk a little bit about genomics. Maybe there'll be later talks that will briefly mention genomics as well, but this is an area where we can actually generate a whole lot more data than we used to be in the past, because technology has enabled us to build genomic sequencing devices that are very low cost. So if you look at this picture over here on the top left, this shows the cost per raw megabase of DNA sequence, and you can see that it's reducing significantly. In fact, with the introduction of new technologies like high throughput sequencing and then more recently nanopore sequencing, this cost has been reducing dramatically. And for comparison, you can see Moore's law over here. So we can actually build genomic sequencers that are much, much more scalable in terms of cost today than transistors, let's say. And as a result, clearly, this is important for many, many reasons. I will mention this in a later slide, but we make scientific discoveries and medical health advancements based on genome sequencing. Unfortunately, we're really bottlenecked by data. Basically, we have very good sequencing devices. They're not perfect, but they're actually very good. Unfortunately, the computational bottleneck is very much a data bottleneck today. And there are clearly many, many applications of this. I will not go into a genomics lecture over here, but maybe in a future version of this, we can talk about how genomics can benefit from more data-centric computing and processing in memory. And there are works that are going on in that area quite a bit today as well. So this is an example of a genomic sequencer. This is the Minion device from Oxford Nanopore. And I think of this as a data generator. This is a great data generator, but it's a terrible data analyzer because it generates data and we move the data at least to a close-by laptop, but usually that's not sufficient enough. We move the data that's generated from these devices all the way into big data centers, and we actually cause a lot of data movement in the system. This example is, I think, interesting because basically we have special purpose machines for data generation, for genomics in this particular case, and then we feed the data to general purpose machines for analysis. And at in the process, we cause a lot of data movement. That's what these arrows signify. And also the machines that we design for analysis are usually very slow. So we have very slow and inefficient processing capability on large amounts of data that we move from one place to another at the macro scale as well as the micro scale. We're going to talk a lot about the micro scale today. How do we design a single computer, for example, where you can process the data inside the memory and storage units? But at the macro scale, we're also causing a lot of data movement from one device to another device, or one device to many data centers, and within the data center between devices. And I believe this picture is very similar to many data generators and analyzers today. I give you an example from genomics, but video analytics is another example. We have specialized cameras today that are extremely fast and efficient at capturing video, but unfortunately processing video is slow because we cause a lot of data movement. Web clicks are another example. Everything you do on the web is recorded somehow, and that's a huge data generator. And again, analysis is relatively slow. And you could keep adding to this if you're interested. But basically, that's the data movement problem stems from this particular data generation capability that we have today, I believe, in many, many specialized devices. And I can talk about genome analysis many times longer, but we've actually written a lot of introductory articles to it. If people are interested in going into this field, I believe that these articles lower the barrier a little bit. And this is a more recent article that was invited to an anniversary of this particular journal that talks about a bit more broadly on what we can do with genome analysis and how can we design intelligent algorithms and architectures for it. I'll give you one example. Today, you can use FPGAs, and you can actually have FPGAs that are closely coupled with high bandwidth memory. So, and we actually use these devices together with IBM. You can offload computation to FPGA logic that is very high, that has access to very high bandwidth and low latency, high bandwidth memory, and you can specialize the computation. And we actually examined this within the context of two different applications, weather modeling and genome analysis. And if you actually do the right things in terms of how you offload and what kind of things, how you actually enable high bandwidth memory access to the reconfigurable logic that you reconfigured on a per application basis, you can get significant speed ups. So you can see the numbers over here. You can improve both performance and energy efficiency by an order of magnitude or even more in some cases. So this is what you can do today. So you can see the promise of having reconfigurable logic that's essentially very near memory, which is more memory-centric than processing the data inside the CPU rack itself. Okay, so what you can do more, I'm not going to talk about these at the moment, but you can actually accelerate genomics much more if you actually do near memory computation more aggressively, let's say. And we actually do a lot of in-store near memory computation that I'm going to talk about later on. So I could keep talking about this, but again, we don't have time to talk a lot about genomics. If you're interested, we can talk more later. I will point you to some lectures as well as the papers that I mentioned. But this was just one application. I think genomics is a very, very interesting application, but we see this in many, many domains, as I mentioned. As a result, data today is overwhelming our storage and memory capability, communication capability, and in the end, computation capability. You may have a great computing device that has lots of processing power, but because data is bottlenecking it, that processing power gets unused. I'm going to give you more results later on. And also, data greatly impacts robustness, energy, performance, and cost of the systems that we build. If you go to the fundamentals, a computing system requires computation, communication, and storage and memory. And clearly, we've been designing all of them. But the effort that we put into computing unit is overwhelmingly larger than the other units. And computing capability today is only inside the computing unit, which is a processor. It could be a CPU, GPU, FPGA, accelerator, ASIC. Every computing unit has a separation from communication and memory units. And this, we call this a processor-centric design. So if you look at this picture, in this picture, we have cores. Cores are computing units. And even within the chip that's dedicated to computation, this is a general purpose chip, most of the chip is dedicated to caches, interconnects, other caches, other interconnects, memory controllers, other interconnects. And then outside the chip, there's memory, other interconnects, and other memory, let's say. So if you do the calculation, more than 95% of the single node is today dedicated to structures that store and move data, even though we call these computing devices. Yet the system is still bottlenecked by memory because these structures that actually store and move data are not capable of doing anything to the data. You have to move the data all the way into the computing cores from wherever the data is. And if you don't like my picture, this is a real picture from AMD from a couple of years ago. You can see the boxed area over here is L3 and L2 caches only. This is by no means just all the memory on chip. There's L1 caches clearly. There's global memory interconnect. Basically, most of the chip is really memory. And we're adding more memory. This is great that we're looking into 3D stacking technologies, but these are being used as more and more and more memory that is not doing any active computation. And if you don't like AMD, there's IBM also, as you can see. So I could keep going with all of these. This is Apple. I think of the chip that in the middle as a lot of SRAM, and then we have a lot of DRAM. And then there's the darkness that we don't normally consider, which is storage. But increasingly, it's a lot more important because a lot of the data sets are actually on the orders of the capability, storage capability of storage devices today. Even DRAM is not going to be sufficient very soon. And it's not sufficient in many interesting applications today, actually. So basically, data is overwhelming our machines, even though we're designing machines with lots of data storage and movement capability. So this is one example based on the research that we did with Google 5 years ago at ASPLOS. We presented this, and we showed that more than 60% of the total system energy spent on data movement on important workloads that I showed you on the previous picture. Actually, we repeated the study with Google on neural networks that they use in their edge device. I'm going to mention this later on in the talk. And we find out that especially in very data-intensive neural network models like LSTMs or transformers, you see more than 90%, 99% of the total system energy is spent on the data mode. So memory is a much bigger bottleneck in some of these neural networks that have very large footprints. Okay, so my axiom going forward in this talk will be that we want to design intelligent architectures, and an intelligent architecture should handle data well. So what does it mean to handle data well? I believe that we need to design systems such that data doesn't overwhelm the components that we design. This requires intelligent algorithms, architectures, and system designs across the stack design, if you will. There are also two other directions that I'm not going to focus much on this talk and as part of this tutorial, because they're related to data-centric systems, but they're slightly different. So we want to, for example, design systems that learn from the data, make decisions based on data, data-driven decisions. So whenever you design a memory controller, cache, interconnects, etc., it should be improving its decisions over time by learning from what it has seen. We call these the data-driven architectures, and there's a lot of effort right now going on, especially on using machine learning to make decisions in the system components. That's interesting and exciting. And this is also goes hand in hand with the data-centric computation, because if you actually start using machine learning to make decisions, for example, in the memory controller, you're actually doing a lot of computation inside the memory controller. And that is very much a data-centric system. And you can do other computation as well. The third direction over here is there's a lot of data. Since data is very important, maybe we should really be understanding and exploiting properties of the data and communicating those to the system better, because data has a lot of properties. It has properties in terms of security, in terms of privacy, approximability, error tolerance, compressibility, the locality, and I keep adding to this. These properties are quite semantic properties at the high level. And most of the time, we actually do not even bother to find out these properties. But if we actually find out these properties and express them and provide them to the underlying system and architecture levels, we can actually make much better decisions in the system. I believe this is actually along the lines of a data-centric architecture, and it could make our processing memory systems much, much better, because we could actually distinguish between different types of data. We could prevent different sort of side channels by knowing the security characters of the data. But again, I don't have time to talk about this. I'm not going to talk about it. But basically, these three different directions lead us to more data-centric as opposed to processor-centric systems, more data-driven systems as opposed to designer-dictated decision-making systems, or human-driven systems, if you will, and more data-aware or data characteristic-aware systems as opposed to systems that make component-based myopic decisions without knowing much about the properties of the data that they're dealing with. Okay, so that's what we envision. We're going to focus especially on the data-centric part. But if you look at all of these, this requires rethinking across the stack. If you really want to design a data-centric, data-driven, and data-aware system completely, we really need to rethink the stack. But we should also look at how to get there step by step. So if you're interested, there are papers that we write about this position, let's say. So let me jump into the first part of it, which is data-centric, memory-centric architectures. And if you look at this, what does it mean to be design architecture that's data-centric? We're going to talk a lot about the first one, processing data where it resides, where it makes sense, near memory and sensor structures, for example. But I believe we also need to rethink the design of our system such that we can have very low latency and low energy data access. I think there's a lot more room over here in terms of the design of our memories for this purpose. We should probably think more low-cost data storage and processing, since data is going to be increasing even more than before. And intelligent data management is going to be even more important, because we need robustness, safety, security, privacy, guarantees from what we store in the system, and also cost and performance. So I'm going to jump to the first one, even though I'm going to talk about this last part and low cost and its effects on the first one a little bit to motivate processing in memory, why it's important to look at it today. So I call this processing data where it makes sense. It's not just any one particular place in memory. I believe we need to be processing data wherever data resides or wherever it's generated. For example, sensors, storage system, DRAM, inside the computing chip in the SRAM units. Even today, inside the computing chip, we need to move the data from the SRAM units to the compute devices. Why don't we enable processing capability all over the place, such that these systems act like distributed computation agents and they communicate with each other? And this is not a new idea. So the early incarnations of this idea was in 1960s. As you can see, this is the earliest paper we could find. If you find any earlier paper, please let us know. We're happy to update our works. And it talks about essentially processing near memory in our terminology, as I will discuss. This is another paper from Harold Stone, who might be familiar to the computer architecture community with his seminal textbooks. He also proposed this while he was at Stanford in late 1960s. So what's different today? And there are clearly many, many more papers that have been written in processing in memory for decades. Today, I believe we're in a more special situation because we never had huge problems with our memory technology. And we also never had such a huge demand from applications and systems to do something different or some computation inside the memory. So let's take a look at these both. So we're essentially having a lot of technology scaling issues, even with the best technologies we have today, DRAM, essentially. I'm going to briefly mention the Rowhammer problem, but there are many other technology scaling issues as well. And these issues demand intelligence in memory, demand some computational logic in memory, actually, to make systems more scalable and reliable. On the other hand, on the application and system side, we are having a lot of issues with data access and energy and power, and data movement energy is dominating computation energy today. And we, at the same time, from the user demands, we need performance, energy, and sustainability at the same time. We don't want a trade-off between performance and energy. And I believe we realize that we can improve all metrics by minimizing data movement. So today, our designs are squeezed in the middle. At the bottom, we're having issues with technology. At the top, we're having issues with applications and systems, and they're all bottlenecked by memory in the end. So we need to do something very different in memory. That's why we believe that in-memory computation is much more ripe for adoption today. But we think we need to rethink how we actually enable it in real systems. So that's why I believe we're seeing a lot of these real system demonstrations. Micron was an early comer to this. They had the automata processing engine. UPMEM developed the first commercial chip for processing in memory, and Samsung and SK Hynix and also Alibaba developed their DRAM chips, and Samsung also has an effort with Facebook on accelerating recommendation systems. We're going to talk about these later on, especially Juan will give an overview of these. I'll just mention these right now, and maybe at the end of the talk, if time remains, I'll briefly go over them, but we'll go over these in more detail. And at HPCA, we had a talk from Alibaba talking about their DRAM chip that is designed to accelerate recommendation systems. And today, we're going to have a talk from SK Hynix, their DRAM chip that's designed to accelerate machine learning and data processing in general. Okay, and there are also, of course, many other experimental chips and startups that are not in this picture. There's quite a bit of effort going on in terms of accelerating matrix vector multiplication, for example, using emerging technologies as well as SRAM. And we had a talk about that from IBM Research on accelerating machine learning and other data-intensive applications using their phase change memory chips at HPCA. Okay, so let's talk about these two directions relatively quickly to motivate things. So we have a huge push from technology today where DRAM scaling is not working out well. As a result, the industry is open to new memory architectures, and they're putting logic inside the DRAM to actually fix some of these technology scaling issues. In fact, there's a paper from SK Hynix also at ISSCC this year, which was just last month, where they talked about how they modified their DRAM chips to include some row hammer solutions to fix the row hammer problem. This is the first time a DRAM company is talking publicly about the row hammer problem in a major conference like ISSCC. Okay, so memory technology scaling is not going well. This is our paper that we wrote about 10 years ago to say that, okay, we're going to have a lot of issues with technology scaling in memory, and we should do something about it. We should design systems to actually avoid the memory problem, if you will, or co-design the system together with the memory. And one of our motivations was the reliability problems, and we did some studies. This is, somehow this moved. We did some studies with Facebook. We analyzed all of the memory errors that they have in all of their data centers across the entire world at the time. And we found this correlation in production data center servers. Basically, the chip density that's employed, this is the DRAM chip density that's employed in a server, is strongly correlated with the failure rate of the server. If you really want to know what this failure rate specifies, you need to compute it very carefully. Our paper talks about it. I don't have time to clearly talk about it. But basically, there's a strong correlation between the density of the DRAM chip. The denser the DRAM chip, the more errors you get in a server. And the main reason is because in a denser DRAM chip, cells are smaller, memory cells that store data are smaller, and they're also closer to each other. As a result, there's a lot of noise that's affecting each cell. And as a result, you get more memory errors. And this manifests itself as application failures or system failures and availability problems at the data center level. And we analyzed this in the paper and talked about some solutions. So we also decided to look at these issues more carefully and in a more controlled manner using FPGA-based infrastructure. So we developed these infrastructures that can test memory rigorously. And these are FPGA-based memory controllers. We also open sourced this. Recently, we open sourced a new version of it called DRAM Bender. Some of you may have used the SoftMC version of it. And we did a lot of studies, and we keep developing this infrastructure so that we can understand these different effects. And while we were actually doing some of these studies together with Intel, we've shown that you can predictably induce errors in most DRAM memory chips. And this is known as the DRAM row hammer problem today. I'll briefly give an idea, but this is something that should not happen. And this is a technology scaling problem. Basically, if you keep activating a row in memory, which means that you apply high voltage to it, and then closing it, and then keep on activating and closing, activating and closing, activating and closing, activating and closing a row in memory. This is essentially a read operation in memory. You see that some of the cells that are physically adjacent to the row that you're activating get corrupt. This is clearly not supposed to happen because we're not even writing to any memory location. Nothing should change in memory, let alone rows that you're not even touching. So we call this row the hammered row. We call these rows the victim rows. And we showed that more than 80% of the chips at the time that we tested in 2012 were vulnerable to this problem. And this is an across-the-board industry scaling problem. And if you actually have these errors, it's a reliability problem, it's a safety problem, it's also a system security vulnerability, because someone can take advantage of those bit flips to take over the system or leak private data, etc. So you can actually launch different types of attacks because of those bit flips. And you can see that people are writing articles that say this: forget software, now hackers are exploiting physics. Now, I'm not going to talk about Drovhammer, but you can see a lot of talks about this and papers about this from us and from others. And this is a 20-minute talk from last ASPLOS, actually, one of the workshops at last ASPLOS, where we talked about the 10 years of Drovhammer. There are more developments in 2022, so that's not the most recent talk. But basically, these works show that memory scaling issues are real, and we're going to have more problems in memory. And more recently, we've written more papers. If people are interested, they can look at this relatively recent paper from January 2023 that talks about the most recent research that we're aware of about Drovhammer. Okay, so that was Drovhammer. That's one scaling problem. You can say that, okay, we can solve it. Yes, solving it requires some intelligence in the memory controller. But there are other scaling problems. So, for example, DRAM may not be scaling very well overall. So we may be looking at some other technologies or other types of DRAM. And we may be combining these different technologies such that designing hardware and the software to manage data allocation and movement between these technologies such that we can achieve the greens of each technology as much as possible, while avoiding the reds of each technology as much as possible. This is clearly called the hybrid or heterogeneous memory systems. And clearly, the architecture community has been looking at this for more than 15 years or so. But this requires us to actually have intelligence in the memory controllers. So if you really want to take advantage of the system, your memory controller needs to be a little bit more intelligent and does computation to communicate between the hardware and the software. That's where I'll leave that particular part. So it's clear, I think, that we need intelligent memory controllers to actually overcome some of the key technology scaling issues that we're seeing. I could give you more examples, but for example, Drovhammer is being sold with intelligent memory controllers. I mentioned the SK Hynix paper. And industry is writing papers about it too. As early as 2014, Samsung and Intel, two companies that normally don't talk to each other without many lawyers present, they wrote this nice paper, short paper, to the memory forum we co-organized at ISCA in 2014. And they basically said that we're having a lot of process scaling challenges in DRAM, and we should really be designing more intelligent controllers that can overcome some of these technology scaling issues. Okay, and there are more works that you can read. So we've actually been building these intelligent controls. So if you look at a storage system today, a storage system has a lot of intelligence in it. The NAND flash controller or NOR flash controller has a lot of intelligence to overcome the reliability issues that flash memory has. So flash memory is a memory technology that is fundamentally much less reliable than DRAM, and it essentially doesn't work. Many of the bits in flash memory doesn't work. What makes it work is the intelligence in the controller that does computation to adjust the voltages appropriately, read voltages, for example, and to adjust the bad bits appropriately and hide them from the system software stack. So there's a lot of intelligence that's going on in flash memory. So we know how to design these memories, except they're longer latency, of course. So we need to think about how to design these at the memory system or main memory level as well. So you might say that there are other technologies that maybe these technology scaling issues are interesting, but once you come up with a new technology like 3D X-point or phase change memory or RRAM, we're not going to have these problems. Unfortunately, I wish that wish was true. We've also been working on many persistent memory or non-volatile memory technologies. Unfortunately, all of these memory technologies have some sort of problem that requires intelligence in the memory controller. They have endurance problems, for example, or other reliability problems. So basically, I believe we're stuck, meaning unless we develop some magic memory technology, which nobody knows about at this point. Once in a while, people claim that they've come up with the magic memory technology, but it doesn't pan out. We're going to have problems, and we're going to have continued problems with memory. And we need intelligent memory controllers to avoid failures and enable better scaling. And that was the push from circuits and devices, which is the technology perspective. Now, let's jump into pull from systems and applications. By the way, feel free to interrupt me, Juan, or anyone, if I can hear you, of course. If there are any questions, I'm happy to take them during the talk as well.
If there are any questions, just raise your hand. Not you can ask later as well.
Okay, unless you interrupt me, I'll keep going. So
there are no questions for now, Onur. You can continue.
Okay, thank you. So let's jump into the systems and application side. On the systems and application side, I believe we have even bigger problems. Technology is interesting. We have a lot of problems over there. But on the system and application side, we also have huge problems with data access, energy consumption, and data movement energy dominating computation energy. In my view, we actually have an even bigger responsibility for the future. Do we want a world that looks like this? Or do we want a world that looks like this because of the computing power that we spend on a lot of things, let's say, and data movement? So if we actually, and this is actually becoming serious because the amount of computing devices that we have in the world and maybe in the space in the near future is huge, and there are billions of devices, and it's going to be an even more significant portion of the amount of energy that's spent in the world, and this is going to create all kinds of power and sustainability problems, and it's actually basically going to make our lives harder, let's say. So I believe when we design computing systems, we should be pushing for high performance, energy efficiency, and sustainability all at the same time. I don't think we want to trade off between them anymore. In the past, we used to make a lot of trade-offs. We increase performance by this much. This comes at the cost of this much energy efficiency. Why don't we actually design techniques that both improve performance and energy efficiency? I believe that's the premise of memory-centric computing. Basically, we have data access. That's the major performance energy bottleneck. And our current design principles cause great energy waste because they exacerbate this bottleneck. And they also cause great performance loss. I put this in parentheses. Basically, we have a processing unit and memory units where data is generated or stored. We move data back and forth between the processing unit and the memory units. Clearly, this has some performance overhead. And to overcome this performance overhead, we make our systems very complicated. We actually design a lot of techniques into our processors, hardware, as well as software, like heavy amounts of multi-threading, heavy amounts of prefetching, many levels of caching and memory hierarchy, as I've shown you earlier, heavy amounts of out-of-order execution. And all of these try to reduce the performance loss. Sometimes they're successful. Many times they're not successful. And in many cases, they actually don't do much for us. And we'll see some examples of it later on. So as a result, we are adding more complexity to our systems to overcome the data movement bottleneck. But that complexity is causing even more energy waste. There's energy waste fundamentally because of data movement, and there's energy waste because of the additional complexity that we're adding to our systems to overcome the performance effects of the data movement, but not the energy effects. So I think so we're in a vicious cycle, basically. I believe we're actually compounding energy in this vicious cycle. So whenever you have a vicious cycle, it's good to nail down the problem. And I believe the problem is really processing of data is performed far away from the data today. And that brings me to this picture early on. Basically, we've designed systems for so long to be processor-centric. All data is processed in the processor. Now it comes at great system cost. And we know that it comes at great system cost. This is actually a beautiful one-page paper from Dick Seitz, who was the chief architect of alpha processors. It's titled, "It's the Memory Stupid." And he basically says that at the time they designed this alpha processor, it was able to finish its peak performances 4 instructions finished every clock cycle. But they tested on important workloads where they actually wanted to design this processor for, and they found out that this processor was retiring 1 instruction every 4.7 cycles. This was a database workload. If you read the paper, you will see. So basically, this processor is operating at about 5% or less than 5% of its peak performance. He basically says why? Because it's waiting for memory to supply the data. And this is his words. I expect that over the coming decade, memory subsystem design will be the only, in italics, important design issue for microprocessors. And I agree with that. This is data from my own PhD thesis, my first paper. Basically, we showed together with Intel essentially something similar in the workloads that Intel used to design its cutting-edge processors with at the time. Most of the time, the processor was waiting for cache misses to come back from memory. This is average across many workloads. And if you're interested, you can read more. Now, Google more recently showed essentially the same thing. This is according to Google, their data center workloads, all of their data center workloads. And this is a cutting-edge Intel processor that's employed in their data centers. Most of the time, the processor is waiting for data. And only 10 to 20% of the time, the processor is doing useful work, retiring instructions. And you can read more about this beautiful paper from ISCA 2015. So basically, we have a grossly imbalanced system. Because processing is done only in one place, data moves a lot. And this is energy inefficient, low performance, and complex. And on top of this, we make our systems overly complex and bloated. This is true for accelerators as well, as we will see later on. I believe this is true for GPUs as well. And we have complex hierarchies and mechanisms. And this is energy inefficient, in the end, low performance and complex. So that's why we have this picture that I showed you earlier. Most of the system is dedicated to storing and moving data, yet the system is still bottlenecked by memory because we're not fundamentally solving the data movement problem. So let's take a look at the energy perspective. That was performance. Energy is even worse, basically. This is data that I borrowed from Beldali. This is old data, but the key takeaways remain. This is a 64-bit double precision floating point operation, 20 picojoules. This is a DRAM read or write, 16 nanojoules. You can see the difference is 800x. Well, 800x is a bit too much today, but we're between 100 to 200x, let's say. So we have not really reduced it significantly. That's a very large number. So the question now becomes, how do you, does it really make sense to add two numbers inside the processing chip? Because adding two numbers requires potentially two memory accesses to DRAM. That's at least 2 orders of magnitude more costly than the energy we use to add these two numbers. And then we write back the data back to DRAM at some point. So basically 3 times 800x is actually too much, or 3 times 100x is too much. So how much data reuse do you need to have in these two numbers that you add and the result you have so that you can actually overcome the energy cost of moving data all the way from DRAM to the processing unit? That's a huge number, actually. Actually, Wen Mei Hu has some numbers in some of his talks. I'll borrow that from in the next in later iterations of this workshop, probably. So that was actually a complicated arithmetic operation, 20 picojoules. If you look at a simple arithmetic operation like a 32-bit add, 32-bit is still not as simple. Some neural networks today use 8-bit adds, for example. You can see that it's actually 6400x difference in terms of energy. So basically, and there are other papers that talk about this too. You can read them if you're interested. And in the end, we see data movement becoming a problem at the overall system energy level. More than 60% of the total system energy is spent on data movement on these workloads. And in some other workloads where memory is actually a bigger bottleneck, where data is much larger, you see more than 90 to 99% of the total system energy spent on moving data between processing and memory units. So I will argue that we do not want to move data. If we want to be truly energy efficient, we do not want to move data. And we do not want to rely on locality characteristics, which are not that much to overcome this huge energy differential. So that's why we need a paradigm shift to enable computation with minimal data movement and compute where it makes sense, where data resides and where data is generated, and make computing architectures more data-centric. So this is easier said than done, of course. Now the question is, how do we do that? I'm going to talk about main memory, especially with some also explorations of storage. But we need to really explore wherever this can be done. Memory, interconnect, storage, other interconnect, sensors, caches. Everywhere where we store or generate data, we should really be enabling processing capability, in my opinion. Now, main memory is very interesting because main memory is actually very large today. And many applications are designed to actually fit into main memory as much as possible. It's not going to be as easy going into the future, in my opinion, but depending on the application. But today, people try to do that. Databases, graph processing, media processing, machine learning frameworks, we try to fit them into main memory. Now, wouldn't it be nice if we actually asked the main memory, can you execute this function on this particular data set, let's say, and return me the results? So this is an accelerator model, as you can see. This is not as this is not more fundamental than an accelerator, but even this accelerator is not as easy to build as we will see. But people are building it. That's the good news. So there are many questions over here. How do we design the compute-capable memory and the controllers? What do they do? How can we enable them to be general purpose? How can we enable them to be very efficient and low cost, if possible? How do we design the processors and communication units after this, in light of this? How do we design the software and hardware interfaces to take advantage of this? And then how do we design the system software compilers and languages to make it easier to take advantage of this and maximize the benefits? And I believe we will also need to rethink the algorithms, because the processing capability that's there on the memory side is going to be different, and sometimes fundamentally different, as we will see in the case of processing using memory, so that we will need to redesign our algorithms to actually take advantage of what happens on the memory side. And I believe we actually really need to rethink the theoretical foundations of computing, because so far, theoretical foundations of computing have been very processor-centric. For example, in the if you've taken a theory of computation course, you're counting operations. The complexity of an algorithm is determined by the complexity of the operations and the number of operations or the order of operations that you do in the algorithm. There's nothing about data movement in our computing theory. I believe we need to develop a more data-centric theory to really, truly design data-centric systems. So you can see that this actually spans across the stack. How do you actually design devices to take advantage of to actually do computation? And how do we design algorithms to take advantage of that computation capability? And across the stack, how do you design the entire stack? So clearly, this is a massive task, and it's not going to happen in one day or overnight. But I believe a research community has been progressing, and we cover some of these some of this progress in our paper on archive. It's a book chapter also, but we keep updating on our archive, and we'll keep updating this. And I'm going to use some examples from this work soon. Especially, I'll define processing near memory and processing using memory. These are two fundamental ways of distinguishing between two approaches to memory technologies. But you can actually see a lot more in this particular paper that talks about enabling the adoption. For example, I will not have time to talk about it. We will later talk about it today, but we will not have a lot of time also, I believe. So you can take a look at the paper for more detail. We actually have developed, thanks to Juan, a processing in memory course that we talk about. This is the spring 2022 edition. There's also a spring 2023 and fall 2022 edition. I haven't updated these slides in a while, but you can find a current edition that's going on, that's live streamed on YouTube. And if people are interested, we welcome any participation online. These are all live streamed on YouTube. Okay, this is a good place to ask questions if there are questions. Otherwise, I will keep going, basically.
Questions there? There are no questions for now.
Okay, great. Okay, so now I'm going to define two different approaches to processing in memory. I believe we need to distinguish fundamentally between two approaches, and this is the most fundamental difference that we could find. I believe there are just two types of processing in memory, let's say. Let's take an example. Today, we have the processor here, and then the memory here. They're far away from each other, right? Processing near memory, the second one, says, let's put the processor closer and closer and closer and closer and closer and closer, or some processing functionality, logic, closer and closer memory. It could be inside the memory chip. It could be inside the bank. It could be next to the bank. It could be outside the memory chip in the memory controller. It could be in a buffer chip around the memory chips. It could be in the memory controller in the processing chip. Yeah, but basically, we're putting logic near memory in this particular case. And this is more traditional, I would say. Basically, we have traditional logic and traditional memory, and we're coupling them as close as possible, potentially with 3D stacking, for example, as we will discuss. And this doesn't fundamentally change the paradigm or programming model, in my opinion, although it does have implications, of course, right? But it doesn't fundamentally change things. Processing using memory is more fundamental, in my opinion. So today we have processor again here, and then memory here. Forget about the processor. We have the memory chip. Can we actually do computation using the way the memory is designed today? Meaning, there's some analog operational characteristics of the memory itself, the way it's designed. Can we take advantage of that to actually perform computation? And interestingly, we can in many, many memory technologies. I'll give you examples from DRAM, but there are examples from RRAM, SRAM, flash memory, and many different memory technologies where you can actually take advantage of the analog operational characteristics of the memory, which is designed as memory, to actually do computation. And you can actually redesign memory such that you can actually do computation even better. So this is a fundamentally different model because this really doesn't have the processor anymore. You actually are using the bit level parallelism in memory and some other things that you may design in addition to it that takes advantage of that sort of bit level parallelism, analog operational characteristics, so that you can actually accelerate applications or redesign the algorithms completely. I'm going to talk about that first. But I believe these need to be combined. Processing near memory is shorter term, and that's why all of the prototypes that are happening in real systems today are processing near memory. Processing using memory is a bit longer term because it's analog operation, and as a result, there are reliability issues, etc., noise issues, variation issues, and that always requires some more time to settle and really adopt in real systems. But let's talk about that first. So processing using memory. I believe this is actually, I believe processing using memory is actually even more energy efficient because you're actually taking advantage of minimal data movements, as we will see. Okay, so what can we do with processing using memory? We're going to take advantage of operational principles of memory to perform bulk data movement and computation. We can exploit internal connectivity to move data. We can exploit analog computation capability, and we can actually add additional connectivity as well as additional capability to do these more reliably or more robustly or better with more parallels. So there are many examples. I'm going to give you examples from the year. And I'm going to cheat. I'm not going to talk about computation. I'm going to talk about data copy and initialization, which is also a problem in modern systems. So in modern systems, we do copying and initialization of data, usually bulk data, for example, when we fork a process or do zero initialization or checkpointing or clone virtual machines, do page migration. So there's a lot of overhead in initialization. Imagine initializing a 10 terabyte memory to all zeros today. Physically, you need to initialize, and that takes a lot of time. And Google, in their paper that I mentioned earlier, showed that about 5% of the entire execution time of all of their data center workloads spent, that 5% is spent in just two function calls, memmove and memcopy. This is actually interesting. Just two function calls are responsible for 5% of the execution time across many, many, many workloads that they use. And they say basically what I'm going to describe next, cloning rows, is a way of overcoming this bottleneck of data copy and initialization. So how do we do data copy and initialization today? If you want to copy a source page, white page, to the gray page over here, you have to go through the processor basically. You have to bring both pages to the processor, do the copying, either in the caches or the memory controller if you're using direct memory access. But you have to exercise this memory bandwidth bottleneck. And that's expensive if your copies are large, especially. So why don't we instead exploit the operational characteristics of memory to move data internally inside the memory chip and bother nothing else in the system? This would be nice because you can do this at low latency, as I will show you, because there's a lot of internal connectivity inside the memory chip. You could do this with low bandwidth utilization because you're not moving data across perhaps the most constrained resource we have in the system today, which is the memory bus. You could basically avoid cache pollution, but you could do that today with direct memory access. And you have basically no unwanted data movement if you want to do this. So I'm going to show you a mechanism that takes us 1,000 nanosecond copy latency, 4 kilobyte page copy latency, to 90 nanoseconds, unoptimized, and 3.6 microjoules spent on 4 kilobyte page copy to 0.04 microjoules. So you can see that the results are quite promising. Let me give you the basic idea. Of course, you need to generalize it, and the paper talks about generalization, but let me give you the basic idea that's relatively simple. So this is a DRAM array that I kind of showed you earlier with the row hammer demonstration. You have a bunch of rows, and then there's a row buffer over here. Now, if you want to copy one row to another row, and the rows happen to be in the same DRAM subarray, hopefully the system software allocated it nicely, you can activate the source row, which brings the data into the row buffer, which are essentially the strong sense amplifiers. Now, you've copied the data minimally, let's say, inside the memory chip. You've not gone out of the memory chip, for sure. And then you activate the destination row, which connects the row buffer to the destination row. And because the row buffer already has strong copy of data, because sense amplifiers are very strong, sense amplifiers drive the data that they captured into the destination row. Basically, by doing two consecutive activates, activate row A and then activate row B, with negligible hardware cost, you can actually do this copy today. So this is called row clone. And this has significant benefits that we have demonstrated. You can actually reduce the 4 kilobyte page copy latency by more than an order of magnitude, and DRAM energy by 70 plus X, let's say. And of course, you need to support it between the banks and between different subarrays. And we have some works that have actually reduced these latencies even more and energies even more that I'm not going to talk about right now. But you can refer to the original paper if you're interested. Now, the interesting thing is you can actually do this in real DRAM chips today. Real DRAM chips that are not designed for this purpose, by violating the timing parameters to mimic these consecutive row activations, you can do row copy. And this is the first work that showed this from Princeton. They went last group, and they used the soft MC infrastructure that we developed. They violated the timing parameters, and they demonstrate that they can clone rows from one row to another row quite reliably in a lot of DRAM chips that they've tested. So this is actually interesting. Now imagine what you can do if you actually design the memory chip to do this copy reliably and across different parts of the DRAM chip. Now, we actually built upon their work to design an end-to-end FPGA-based processing in DRAM framework that can do row clone, as well as true random number generation using off-the-shelf DRAM chips. And we open source this. You can find this on archive, and we have a published a paper on this also. And you can actually use this right now to do this sort of operations. We evaluated, for example, how to do page copy and how to build the system software stack for it. And I'm not going to talk about this because later there will be a talk from Ataberk who will discuss this is the infrastructure that he led building. Okay, and you can find a lot more information on how to actually make data copy and initialization more efficient using DRAM with additional optimizations that I'm not going to talk about right now. But you can see that this our mindset right now is memory is an accelerator still, and we're accelerating, we're adding some specialized capability inside the memory for data movement in this particular case. And
you don't need to add much, essentially, because there's a lot of data moment paths today. Of course, for example, between two different subarrays today, the path exists, but it is very convoluted. If you actually add some more direct paths, some more connectivity between the same subarrays, you can actually do data movement much, much better in today's DRAM chips. Okay, so that was kind of cheating. This is data movement and initialization, extremely important in modern workloads. Unfortunately, it's not computation. So what can we do in terms of computation? Basically, we've also shown that you can do in DRAM AND, OR, NOT, and majority functions bitwise, in a block bitwise manner at low cost. And we're going to use analog computation capability of DRAM, just like we did earlier with row clone. And the idea here is right now to activate multiple rows to perform computation. And we see significant performance energy improvements. And this is the paper that introduced the idea. And I believe new memory technologies enable even more opportunities. And because these can be designed to actually do this better, and also because the reads are not destructive like they're in DRAM, they can operate on minimal data moment. I'm going to briefly mention this in the later after I talk about DRAM and flash, and then we're going to move on to processing near memory. But there's a lot of space over here that opens up once you consider internals of a DRAM chip and the analog computation capability that could be present in these chips. So let's take a look at how you can do AND and OR more generally, bitwise majority function in DRAM. Assume that these are 3 rows in DRAM. I'm not showing you the entire row. I'm showing you only one cell in each row. But normally you have 8 kilobytes, for example, of data in a single row. So you're going to do this operation on 8 kilobytes of data, and it can replicate on thousands of subarrays, let's say. So if you concurrently activate these 3 rows, what happens is concurrently those 3 rows, 3 cells get connected to the same bit line. Now, based on chart sharing principles that you have on the bit line and the capacitor, if at least 2 of these cells are charged, the end result is the charge state on the bit line. Now, if at least 2 of these cells are discharged, the end result is the discharge state. Now, this is essentially the description of a Boolean majority function, bitwise majority function. Basically, activating 3 rows concurrently, circuit theory says that you should get a bitwise majority function. And that's what we see in simulations as well as real DRAM chips. Now, bitwise majority is a beautiful function on its own. Actually, Donald Knuth has a nice chapter dedicated to bitwise majority. But if you set C to 1, you get the OR of A and B. If you set C to 0, you get the AND of A and B. So you can have bitwise OR and bitwise AND. Now, this is also nice. It's not functionally complete. To make it functionally complete, you need an inversion. And inversion actually exists, but it requires changes to the DRAM chip a little bit more. And the idea is basically, you can see that once you read one cell, the complement of the value exists in the other side of the sense amplifier. We propose to actually take that value and feed it back to the array in a special row. And that row can be used to take the complement of a row that you activate. So you can actually do the inversion that I don't show here, but we actually talk about that in the Ambit paper, not this particular computer architecture letters paper that I mentioned over here. Now we can actually do bitwise majority, bitwise not, bitwise AND, bitwise OR. You can build anything out of this because this is functionally complete, right? Now, what do you do with it? Of course, there are some algorithms that are much better fit because we're doing bulk bitwise computation. And there are actually algorithms designed for bulk bitwise computation. For example, bitmap indices that are commonly used in databases. The bitweaving database that was developed in 2013 by Jignesh Patel's group. Microsoft has the Bitfunnel web search engine. And I could keep going on. So there are some algorithms that are a good fit for this. But I believe you can actually fit any algorithm to it. And we're going to talk about that after what I'll show you. So we adopted the bitweaving database, and we actually simulated it in our simulation infrastructure. And we showed that you can actually get 4 to 12x performance improvement if you actually take advantage of Ambit, these in DRAM majority, not bitwise AND or OR operations in a nice way. And the paper has a lot more results. I just don't have time to cover it. So this is actually interesting now, I think, because now you can have bitwise execution engines. Now, how do you make it more general purpose and programmable? That's what we targeted next. This was presented at ASPLOS 2 years ago. We call it SimDRAM. I'll give you the basic idea. Here, user actually can express any desired operation using AND or NOT logic. It's like a circuit, if you will. It could be a convolution operation. It could be matrix multiplication. It could be arbitrarily complex. First, we generate majority and NOT logic, which is actually more efficient to this for this, because majority and NOT also is functionally complete. And we actually take advantage of some quantum computing design automation system designed by EPFL in Nani Demicheli's group to actually optimize the circuit. And then in the next step, we generate the sequence of DRAM commands, triple row activation, consecutive row activation, pre-charge, etc., to execute this particular operation in a bulk bitwise manner, of course. And then we associate that microprogram, if you will, sequence of DRAM commands using a new instruction in the ISA. And that new instruction in the ISA can be called by a program. Essentially, the program uses a PIM-enabled instruction, and this instruction gets shipped to the memory controller when it gets called, when it gets executed. And the memory controller executes this microprogram that was optimized by our optimizer to, for example, do a convolution operation. It could be any operation. It could be just a simple multiplication as well. And in the end, the result is in memory, and then it can be read by some other instruction or some other bulk bitwise operation in this particular function that someone designs. So we believe this actually reduces the barrier to adoption. This also improves performance. And there are actually papers that do compilation more recently on this sort of bulk bitwise engines. There was one at HPCA, for example. Okay, I will not go through this in more detail. You can certainly read the paper, but we actually evaluate this on 16 complex in DRAM operations and 7 real-world applications. And we see significant benefits compared to CPU and GPU in terms of both throughput as well as energy efficiency. But you can see that the energy efficiency numbers are actually a lot higher because you gain some throughput, you gain some performance clearly, but energy efficiency, you gain even more because there's no way of saving the energy in a CPU and GPU in general. Unless you can exploit a massive amount of locality, which is not easily present in many applications. Okay, so that's SIMDRAM. So we actually improve this sort of work to do more complicated operations in DRAM. I don't have time to talk about it, but by adding more modifications to DRAM, like doing lookup table-based computation, you can actually do even better. And I'll refer you to the paper. In real DRAM chips, we've shown that you can exploit the latency reliability trade-off by violating the timing parameters. You can actually generate a signature of the DRAM device, which could be used as a physical unclonable function, which could be used in remote attestation. I think going forward, including security functions inside memory and inside processing in memory systems is going to be important because we'll be, if you actually move the data as little as possible in a system, you can also reduce the vulnerability of that data to security attacks. A lot of the security attacks, in my opinion, are actually caused by data movement in the system also. And we can actually do a lot of things on the memory side, but we need to do that securely. So physical unclonable function is important. We also shown that you can actually do random number generation, true random number generation by violating the timing parameters. And some cells fail truly randomly in this particular case. And we demonstrate that on real DRAM chips, many real DRAM chips. And the PyDRAM infrastructure that I mentioned earlier, that's going to be described in more detail by Ataberk later today, is capable of doing this D-range, and it's open source, and you can test it for yourself. And of course, there are other ways of doing true random number generation that are better than what we have described earlier, but I'm not going to go into that. Okay, so I should also say that DRAM is very, very interesting, but Flash is also very interesting. In fact, Flash may be more interesting because you could do this operation, this bulk bitwise execution on even larger amount of operands. And in this particular paper, we've shown that you can, for example, do a 32 input or 48 input AND as opposed to just a 2-input AND in a bulk bitwise manner. And you could do this reliably. So, and we have data from real DRAM chips that we demonstrate in this paper. So I think the capability of real flash chips, capability of real memory chips, DRAM chips, flash chips, of doing computation is very fascinating. And the compute DRAM paper that I mentioned earlier actually showed that in a fraction of the DRAM chips, you can do the bulk bitwise AND and OR operations that I mentioned earlier. So existing DRAM chips, existing flash chips are actually capable of doing this computation, even though they're not designed for this purpose. You just violate the timing parameters or play some tricks to actually show that you can actually do this computation. Now imagine what you can do actually if you can design these chips more reliably to do this computation. Now, I will quickly mention emerging memory technologies, non-volatile memory. So similarly to our work, people have shown that you can actually do bulk bitwise operations inside phase change memory, for example, non-volatile memories. It's relatively similar to what I described. Multi-row activation is the primitive. And in memory, these technologies, some of these technologies actually have cross-buy array structure, which enables other operations that are not possible in DRAM in its current form. You can use these cross-buy arrays to perform dot product operations using the analog computation capability. Basically, you're taking advantage of, again, analog computation using Kirchhoff's laws. The fact that bit line current is a sum of products of the word line voltage times the conductance in the cell, in each cell. Okay, so I will not go into this in detail, but that's the idea, this Kirchhoff's laws. You can, for example, store the weights of a matrix over here and you can input the vector that you want to multiply with the weights in the matrix. And the computation happens in the analog domain using Kirchhoff's laws based on the voltages that you input and the conductances that are stored over here, resistances that are stored over here in the cells as weights. And then you need to do analog to digital conversion, of course, in these chips to actually make sure that that works nicely, let's say. So this is also happening right now. There are a lot of prototypes that are designed. Actually, ISSCC conference has many prototypes this year as well that talks about this sort of computation in RRAM cells as well as SRAM cells. I will not go into the details of it, but I believe this is also fascinating. And again, I have some animations here. These slides will be available, but we just don't have time to cover all of this since we're almost at the end of the talk. Okay, now I'll jump into processing near memory. Again, if there are no questions. As I said, processing near memory is fundamentally closer to...
Onur,
oh, there's a
there is
question.
one
Okay.
question.
Okay, please go ahead.
I think we can use it.
Thank you. Sorry for waiting up the presentation. With all of the processes using memory, I've read most of the papers you mentioned, but I've been wondering how robust are these things in terms of surrounding temperature, possible voltage fluctuations. Do you have any experience how these really large effects might actually affect your computation quality?
Yeah, I mean, I didn't quite understand the question, but I think I understand the gist of it. Basically, how robust are these operations to temperature, voltage, variation, etc.? And that's a wonderful question. I think this is the area of research where we should go into. And this is why I said processing using memory is actually longer term, because we really need to understand the robustness of these operations. Certainly RRAM, for example, even SRAM, there are a lot of robustness issues. And there are some studies that talk about this in ISSCC, for example, all those conferences, but we need to do more. Usually they're used for applications that do not require, let's say, full robustness, for example, neural network inference. So that's the showcasing application for these. But in our experience for DRAM and flash, there are also robustness issues. So I'll not go back to those slides, but there are also robustness issues in our experience. It's not perfect, let's say. We report some of these numbers in terms of variations in some of our papers, both in terms of real chip results as well as circuit simulation results. So that's an area we really need to work on. So that's an excellent question. I do not have a, let's say, perfect answer to you, because that requires a study of a very wide range of, let's say, temperatures, voltages, and many different use cases, different types of variations, etc. That study needs to be done. No question about that.
I don't know, it's Mark from Technion. Great talk as usual. I was wondering, I would like to follow up on the previous question to some extent. The analog nature of the computations imply that in order to perform them, you need to first kind of transform the data into analog form, then basically perform them, and then do the deck again. So to what extent this actually inhibits the benefits of this architecture?
Yeah, that's also a great question, Mark. Thanks. So I think that's not, in my opinion, that's not that bad, especially in DRAM and flash, because in DRAM and flash, you're really storing bits, right? The bits are stored just like you are you're interpreting them today. It's 0 or 1, basically. It's not an analog value in that particular case in DRAM or flash, at least the way we proposed it. In the RRAM-based systems, yes, absolutely. Basically, the weights are represented as an analog resistance value, and now you need to certainly convert the weights to an analog resistance value, and there's some procedure that you need to go into for that, and I believe that that requires some even more understanding than what we have for DRAM and flash. So again, I don't have a perfect answer. There are works that are going on. So for example, at ASPLOS, there were works not in this particular domain, but more on analog computation in general and how to represent analog values for like an analog hardware for computing. Sarah Ochur, who's at Stanford right now, she did this work while she was at MIT, talks about some steps on actually how to do this in a more robust manner, and also talks about some programming language support. I'll refer you to that. Maybe you're aware of it. But again, I believe we need to do a lot more work in that area. We're not done yet.
Okay.
Thank you for the talk. I just have a small question regarding the you say bitwise operations between rows. You mentioned that it is possible to do, let's say, a simple and or operations between rows by activations. Would you use that to do actual XOR or carry adding stuff within the memory with the multiple activations?
I'm sorry, I lost you. Would you use that for what?
For doing actual binding actions like XOR or carry something like that.
Yes. Yes, certainly. You can use those. Let me go back to the SIMDRAM framework. So this is what we show in the SIMDRAM framework. Basically, in this particular case, we show that you can use any operation and optimize it as well using this framework. So essentially, this desired operation can be anything. It could be XOR, it could be XNOR, it could be something more sophisticated like multiplication, division, etc. But if you're asking if you can do XOR natively in DRAM, we don't know a way of doing that right now. So natively, we don't know, but you could build on majority, not, or and or not.
Right. So I haven't read the paper, but since it's a bit serial approach, so you have to serialize the thing first.
Sorry, I couldn't understand that also. You're a bit far and choppy.
I haven't read the paper, but it seems you have to, it's a serial operation, not like that.
Okay. Okay, I mean, if you have a paper, please send it to me. I'd love to take a look at it.
Yes. So, sorry, I think you didn't understand. Well, it's asking that the computation is bit serial.
Oh, the computation is bit serial.
Yeah, so his concern is that the computation is bit serial, right? Because we operate on individual bit lines.
Yeah, exactly. So again, in this SIMDRAM framework, you can take advantage of the bit serial computation to do multiple bitwise, because you're actually taking advantage of the vertical data layout. Again, I don't have time to go through it, but maybe Juan will have more time later on today to describe it. But again, it should be said that if your data widths are large, let's say 64 bits, of course, bit serial operation is going to take longer latency at some point. So you can think of this as, I don't know how many people remember the connection machine over here. Probably there are some people, I don't see the room. But connection machine had a similar idea, right? In the 1980s. Their idea was to have 64,000, 64K to be more exact, bit serial processors. And they basically had bit serial addition, bit serial operations to maximize parallelism across those operations. But each individual operation took long. So there are cases where you actually do this sort of operations. You're basically tolerating latency for throughput of the operations. And in memory, you have a lot of throughput, but your latency increases as your data width increases. Now, of course, we should not be satisfied with this. There are other ways of actually improving this that we are working on, and I believe other people are working on, to make the latency of operations even shorter. Okay, great questions.
Yeah, I think there are no more questions for now.
Okay, do we have time? Or maybe I'll go through this relatively quickly.
Yeah, I guess it's time to wrap up probably.
Okay. I mean, I'll talk about the more traditional, let's say, processing near memory approach. We'll talk about this more clearly, and existing prototypes exist for this. But I'll give you some what we're thinking about. Essentially, we're still thinking about memory as an accelerator. Then this question becomes, what can we put close to memory, and how do we put it close to memory such that we can accelerate important applications? I'll give you our experience. We started doing this work in around 2012 or so, even earlier actually. And we were looking at in-memory graph analytics. And we were looking at graph processing, because graph processing is very much memory bound. There are frequent random memory access and little amount of computation to cover for it. And we designed this system based on 3D stacking technology. Essentially, you have a logic layer and then memory layers on top of it. And this is nice because the logic layer can have anything really built if you actually really truly design it as a logic layer. And that can be connected, to the memory layers with high bandwidth, low latency, and low energy connections. And we designed the system that's called Tesseract for graph processing. There's no time to go over the details, but it's essentially a distributed system of accelerators. And each accelerator is this 3D stack cube, let's say. In each cube, you have a distributed system of in-order cores.
these in-order cores, each in-order core contains performs operations on the graph locations that are stored on the memory on top of it. Essentially, we partition the graph across these cubes first, and then across the in-order cores in each cube. And then whenever you want to compute something or update a graph node, we need to send a message to the in-order core that houses that graph node on the memory stack on top of it. So essentially, this is remote procedure call-based programming. We don't move data, well, except for intermediate values, of course, but we do updates in a way such that the updates don't move. And that's the idea, basically. We use remote function calls based programming, similar to distributed system programming that's done in data centers today. And we have some prefetching mechanisms. And the idea is you can offload your graph computation, hopefully nicely, to this distributed system. And the graph computation happens hopefully with minimal data movements. But of course, sometimes the graph, you need to send messages across these chips, and that's where things get expensive. So your graph partitioning matters, your optimizations matter. And our initial work was promising. We basically compared this to processor-centric systems. And you can see that the processor-centric systems all have the processor and memory dichotomy, whereas Tesseract doesn't have it because processor and memory are together, and you have a distributed system of processor and memories that are tightly coupled to each other. And as a result, each processors are exposed to very large amounts of bandwidth. This is 2013 numbers or so, which is quite large, as you can see, more than an order of magnitude compared to the best prior system at the time. And we see that over 5 graph processing algorithms, you get significant performance improvement end-to-end. And this is work at the time. Later work actually improved this. They basically optimize the graph partitioning, for example, load balancing, interrupt handling, etc. And I believe the numbers are closer to 100x right now in terms of performance. And our work showed that you could actually get significant energy reduction. And future work actually after this showed that you could actually get closer to, let's say, 2 orders of magnitude. So I think there's a lot of potential, as you can see, once you start optimizing. I'll give you another example, more from the storage systems. This was published in last year's ASPLOS, GenStore. I'll give you the basic idea very quickly. So today, what you do in genome sequence analysis, you move data all over the system, basically, from storage all the way into the computing unit, through the main memory and through the caches. And you do some sort of analysis, let's say alignment. There's computation overhead in the analysis, and there's data moment overhead. So to solve computation overhead, there's a lot of developments that have happened, heuristics, accelerators, and filtering mechanisms. So today, we're not bad at computation overhead, but we're still not good. But this has exacerbated data moment overhead. So if you have a very good accelerator, for example, for computation, data moment overhead becomes a much bigger fraction of the execution time. So here we wanted to actually do in-storage filtering such that we minimize the data moments and reduce the energy cost of it at the same time. And that's the idea over here. We filter the reads with specialized logic in the storage system, minimal logic. We don't change the flash chips. We change the flash translation layer a little bit. And the hope is that you don't actually send a lot of things to the main memory caches and the computation unit. And we validate this using a bunch of data sets that we discuss in the paper. And I don't have time to go through it. And this reduces the data moment overhead. And we see significant speed up as well as energy reduction at the same time. So we don't have this speed up versus energy trade-off. So I think this is going forward, we need to do more in the storage system because storage actually is huge. And there's actually a lot of applications that exercise storage. And this is one example from a genomics domain. Of course, there are other examples that other people have shown in terms of graph processing, for example, and other data-intensive applications. So I'm going to skip this, unfortunately. I don't have time to talk about it. This talks about the work that we've done with Google. Here, we offload specific functions to memory. And we get lower benefits, but this is actually more adaptable because data moment actually often comes from simple functions. And again, there are a bunch of functions that exist in many different programs. And this is TensorFlow Mobile, for example. Okay, so I can give you more examples, but I will not. There's a lot you can accelerate by taking advantage of processing near memory, like we have shown, and processing using memory. Some of these cases, we also talk about processing using memory as well. I will just point you to a paper that we've done with Google on neural network inference. Here we studied real neural network models from Google, and we categorize them. These are edge models. We categorize them in terms of their variation of the layer characteristics. As you can see, there's a huge variation in terms of flops per byte and parameter footprints in different layers. And there's also a huge variation within a layer as well. So instead of designing monolithic accelerators like we do today in machine learning, we argue for designing heterogeneous accelerators that are catering to different types of layers. And we designing runtime systems to decide which layer, which accelerator which layer should be executed on. And again, this is a proof of concept. We believe there needs to be more done in this direction, like highly identified layer families. But the interesting thing is some of the neural networks like LSTMs, we don't have that in this picture, but for example, we show that some of the neural networks here, LSTMs and transducers, they are very much memory bound. Most of the energy is spent on off-chip interconnect and DRAM, as you can see. And by having data-centric accelerators on the memory side, you can actually reduce the energy significantly. And there are throughput and latency results in the paper that I will not talk about, but you can take a look at the paper. This paper also shows that you can reduce the area dedicated to accelerators significantly if you actually design 3 accelerators that are more specialized than a single accelerator that's trying to do everything, but not doing memory-centric accesses, memory-bound accesses very well. Okay, so this is where I'll land. I believe we need to revisit the entire stack, but we can get there step by step. And if you're interested, there's more in our papers. I think Juan will later talk about adoption, and there's a lot of adoption issues, and I think a lot of them relate to topics in ASPLOS, I would say. That's basically applications, software, programming, system and security issues, runtime and compilation systems, and infrastructures. I believe more importantly, we need to change our mindset because our mindset is very heavily ingrained to compute-centric designs today. We should move from that mindset to data-centric designs and basically have a clean slate for designing computing going into the future. Okay, I will let me go to the final slide over here. I'm happy to take questions. I don't know if there's time for questions, but this is exactly why processing in memory is happening today, and we will talk about that more today. Okay, Juan, I think you can take over. With these slides will be available to everyone. I'm happy to take any questions. Maybe I'll end with this one because I'd like to foreshadow the SK Hynix talk because they're designing very interesting systems to accelerate, especially machine learning today.
Yeah, okay, thank you, Onur. Thank you for the great talk. Are there any other questions in the room? One. Yes.
Hey, Onur, this is Danny from Rambus. Very interesting talk. And I have more of a comment than a question. You know, taking kind of a new holistic look at the entire architecture stack, I think it's really interesting the abstraction that you made for, you know, the concept of data, not just memory, not just storage, but rather data. And obviously there's advantages from computation in memory, using memory, in memory, near memory. And I think the same abstraction can be made for storage. Using storage, in storage, near storage, etc. And then obviously there's some advantages, you know, if we look at the entire stack, if we can abstract, you know, say an instruction set that says, you know, here are some instructions for in memory, here are some instructions for near memory, here are instructions for in storage, near storage, etc., such that we can get the advantages of reducing power across the interconnect, whether it's direct attached memory or interconnect to storage, etc. I do want to throw a bit of a wrench in the mix, though, and that is security, right? Obviously, the concept of a row clone is very attractive from a performance and power perspective, but then obviously, you know, in the cloud, we have multiple VMs for multiple users sharing kind of the same memory, and we don't want user A cloning user B's data. And so obviously, I think at some level, we're going to have to start talking about what sort of storage or what sort of security hooks we need to put into these different accelerators at different places in the stack. I do some work at OCP's AI hardware software co-design, and you know, we're also working on some of these topics. I encourage some of your research group or anybody here that they're interested to also be attending some of those OCP calls. Very interesting. But thanks a lot, Mark.
Yeah, thank you for the comment. I mean, I agree with a lot of things you said, and I agree that security is important, and there needs to be more investigation of how to take advantage of in-memory computation mechanisms for security, for improving security, as well as how to make sure that new security issues do not arise
because of some of these mechanisms. And yeah, certainly there needs to be more work in that area. Thank you.
Hi, this is David. I have a follow-up question. What we can see in the whole machine domain with confidential computing is it's moving all into the direction of encrypted memory so that you have full memory encryption. How applicable do you think are these approaches when it comes to encrypted memory?
Yeah.
Where it's really the whole logic of the memory encryption is handled by the CPU and not by the memory.
Yeah, so that's an excellent question, I think. So basically, how do you do the computation in an encrypted manner in memory? And that's something that I think that's also future work. I mean, this is a tough question for many systems, but I believe if we can do encrypted computation using the CPU, we can also add encryption mechanisms to the memory side. There are some works in that area also, but there needs to be more work, I believe. Certainly, encryption complicates things, right? Because you cannot do, let's say, bare computation like we have described so far, at least in analog. Processing near memory is more amenable to this, right? If you do processing near memory, you can have an encryption engine also near memory. So it doesn't affect processing near memory as much. But if you do processing using memory, now encryption needs to be thought about carefully.
Thank you for the answer. Are there any other questions? Okay. So then I guess we are done.
Okay, thank you. We have a good coffee break.
Yeah, thank you, everyone. We will continue after the coffee break. We will have the lecture about processing near memory architectures.
I will stop sharing my slides then. Maybe you can put up what you would like to share, Juan.
Sure.
Me. Maybe I should say something. The questions are not easy to hear. You're hearing me properly, right?
Yeah, we can hear you well.
Yeah. The questions I tried my best to hear, and I think I got the gist of most of the questions. But there's depending on where the person who's asking the question sits, I believe there's a lot of either echo or not so clear.
Yeah, well, everyone was using the microphone, and you were listening to them through the speakers in the room.
Yeah, I see. Yeah, I mean that's a fundamental issue with the room. Maybe
Yeah.
you're perfect. Like when you're close to the computer, it's perfect. When you go away from the computer, it also becomes worse. So.
Yeah, exactly, because the Zoom is capturing from the microphone of my computer. There is no way of connecting the microphone in the room to the computer. I asked the technician earlier.
I see. Okay. Anyway, just so that you're aware. So Hynix people, for example, may need some help with let's say the questions, right? They may not capture it.
Yes.
Easily. Okay, great. I'll stay.
muted.
Okay. Thank you, Onur. I'm not going to stop the live stream.
Yeah, I think you can keep it going, right?
I will just keep it, and I guess we'll be back in about 10 minutes or so.
Sure, sounds good.
Okay, yeah, I guess if you guys are ready, I think we can continue with the next talk of the tutorial. We'll have this until what time exactly? The lunch time, I think is 20. Okay, 12, yes, exactly. Sorry. Yeah, okay, so yeah, we have more or less 1 hour and 10 minutes or so. So I think we have a good amount of time to go over many slides. Probably I will not be able to finish the entire presentation, all the slides I have, because the presentation is very comprehensive, I would say. But yeah, for sure, it will be enough to give you a good overview of processing near memory systems that already exist. We can call them real processing near memory architectures. And we are going to have a strong focus on the HBM-PIM architecture, which was the first architecture to be commercially available. But we will also talk about the other ones, prototypes from Samsung, SK Hynix, and Alibaba. And I will give you also some pointers to lectures where we talk more in detail about these architectures. Anytime, feel free to ask questions. Yeah, it will be nice to have discussion over the course of this presentation. Okay, so let's go ahead. First of all, remind you the two processing in memory approaches that Professor Mutlu has already introduced in his talk. We can distinguish between processing using memory, where we directly use the analog properties of the different memory components, as DRAM cells might be, in ideas such as row clone or ambit that Professor Mutlu presented. And we have processing near memory, essentially when we place some sort of compute unit or processing memory processing element near the memory arrays. This can be different types of memories like SRAM, DRAM, or the storage, and the type of processor or the type of processing element that we place there can also be pretty different. We can have more general purpose cores. We can have more parallel units such as SIMD units, or maybe even small GPU cores in some of the proposals. But as I said, processing in memory is becoming real, and the first company that announced that they were going to commercialize a real processing in memory system was UPMEM back in 2016 or so. They announced it, and in 2019 they started to commercialize. We have been pretty lucky that have been working with the real UPMEM system and for the last 2-3 years, and have already published a good amount of work that I'm going to introduce at least today. As I said, there are also more recent prototypes from Samsung, from SK Hynix. It was Samsung in early 2021 in the ISSCC conference that they announced what they call first FIM-DRAM, or function in memory, or function in DRAM, and then they call it HBM-PIM. I'm going to show you a couple of slides about that as well. Later in 2021, Samsung also announced a DIMM-based prototype, a DIMM-based solution that is called AxDIMM, and I will show you a few slides as well. And last year, about a year ago, SK Hynix presented the accelerator in memory architecture, or AIM, that today they are going to explain, hopefully with a lot of detail in the talk that we will have in the afternoon. And the last one here is Alibaba this accelerator, HBM-PIM for recommendation systems that they presented also 1 year ago, and they delivered talk in the tutorial that we organized at HVCA. So let's start talking about HBM-PIM. Because it's the first one that was publicly available, and also because it's where we have been doing a lot of research recently. This is a slide from Professor Mutlu, and here you can already see the first picture of this HBM-PIM architecture. As you see, it looks like regular DIMMs. It looks like regular DDR4 DIMMs, where we have 16 chips, typically divided into 2 ranks of 8 chips. And the key difference with respect to regular DDR4 memory is that inside each of the chips, there are not only memory arrays or DRAM subarrays, but also there are small processors, small in-order processors that are called DRAM processing units or DPUs. Here you can see another view of these DIMMs and how they look. The very first prototype that we were able to work with was this E19 with only 8 chips per DIMM and pretty slow DPUs running at 267 megahertz. More recently, or sometime later, they started to produce the DIMMs with 2 ranks, 16 chips in total, and running at a higher frequency, 300 megahertz, the first generation. The current one is running at 425 megahertz. And this is a picture of the real HBM-PIM system with 2560 DPUs. As you can see on the slide, well, as you can see, I will go in detail soon about how the overview of the system itself, but here in the picture you can identify the dual socket CPU, CPU 0 and CPU 1, and then next to them we have DRAM memory, conventional DRAM DIMMs, because the system still has conventional DRAM DIMMs that operate as the main memory, and the HBM DIMMs that are the PIM-enabled memory. For all the details, I will show you this slide later again, but for all the details about our first work on characterization and understanding this real-world architecture, here you have the links to the archive version of our paper and also the repository. But let's start taking a look at what HBM promised when they filed a patent in 2019. What the abstract of the patent says is that this is a memory circuit with a memory array and a first processor. This first processor is the near memory processor, what they call DPU. And there is a control interface for a central processor to communicate with the first processor. The central processor is what we are going to call the host, which is a CPU, the regular CPU and Intel Xeon in the slide that I showed you earlier. And these memory banks become accessible to either the host processor or the DPUs. Here you can see also another picture from the patent. This is describes the PIM system organization. This is the host processor, a system on a chip or a CPU, and here you can see the DRAM chips with the memory arrays and the small processors near each of the memory arrays. So basically, the HBM-based PIM system contains a host processor, a host CPU, some DIMMs or regular DRAM memory that are the main memory, and some other DIMMs that are the HBM DIMMs, the PIM-enabled memory. We can take a closer look here at what we have inside each of these PIM chip. As I said earlier, each HBM DIMMs contains 8 or 16 chips. One rank is 8 chips, and inside each PIM chip, there are, as you can see here, 8 DRAM banks of size 64 megabytes in the current generation. In the HBM terminology, this DRAM bank is called MRAM or MRAM bank. And so we have 8 of them inside each chip. And next to each of the DRAM banks, we have the DRAM processing unit. So in total, there are 8 DRAM processing units per chip and 64 per RAM. We can go more in detail about the DRAM processing unit. This picture also comes from the patent. And here you can see again the different memory banks, M8 in our previous slide. We can see here the memory bank and then the pipeline, the DRAM processing unit. As you see, it's composed, it contains an instruction memory, a pipeline, and a local memory. We are going to see more about this. So here you see the internals of the PIM chip. These are the control status interface for the host to communicate with the DPUs, the DDR4 interface for the host to access the DRAM banks, because of course the host, as you will see, has to write data and read data from these DRAM banks before and after the DPUs do their job. Here you can see the 64 DRAM banks or MRAM banks, and connected to them, or the access to them, happens through an DMA engine. So it's the access to this MRAM is asynchronous with respect to the execution of instructions in this pipeline. As you can see, the DMA engine is going to move instructions between the MRAM bank and the IRAM of size 24 kilobytes, an instruction memory. Observe that is not an instruction cache. It has a size of 24 kilobytes, and this means that the maximum size of the kernel, the function that we run on the DPU, is limited. In total, if I recall correctly, is 4,096 instructions. And then at the bottom, you can see this WRAM. It's an SRAM-based memory of size 64 kilobytes. It's a scratchpad memory or a software managed cache, so it doesn't operate transparently. The programmer should explicitly move data from the MRAM bank to the WRAM and then results back from the WRAM to the MRAM for the host to access those results. The DPU pipeline, as you see on the left-hand side, has 14 pipeline stages. There are some registers, not many, and here you can see it with a little bit more detail, a little bit closer. As I said earlier, this is an in-order pipeline. It runs at a frequency of up to 425 megahertz in the current generation. I think that next generation frequency will be a little bit higher, maybe about 500 megahertz, as I have heard. And it's a fine-grained multi-threaded pipeline. It can run up to 24 threads. And that number is important, but rather than the 24 hardware threads, it's important to understand that the number of threads that we want to run simultaneously in the pipeline is related to the number of stages that we have in the pipeline. As you see, 14 pipeline stages, they are pretty similar to what we could expect in other pipeline, like MIPS, for example. There is a step or a stage for thread selection, because it's a fine-grained multi-thread architecture. In every single cycle, we are going to launch an instruction from a different thread. Then we have instruction fetch stages, register file stages to access data, access operands from the register file, operand formatting, ALU stages, and finally the result formatting stages. During the ALU stages, we can either use the ALUs. We will see what are the instructions that are natively supported by this pipeline, but we can also access data operands that reside in the WRAM. Remember, we first need to move the operands, the input operands that we are going to use from the MRAM to the WRAM, and then the pipeline can use that data. Just for you to refresh, if you need it, about fine-grained multi-threading, there are a couple of slides here. Fine-grained multi-threading is just a technique where we basically switch to another thread, to a different thread in every single cycle in order to avoid dependencies in the pipeline. This simplifies a lot the design of the pipeline because in order to be productive, we don't have to include data forwarding unit or data, or in order to avoid dependencies, we don't need to install the pipeline, etc. But yeah, these are a couple of slides, but if you want to refresh more about fine-grained multi-threading, here there is a link about one lecture from Professor Mutlu. So this is the DPU pipeline. This pipeline is a general purpose. It's 32-bit. It supports a 32-bit ISA. It's a RISC ISA, but it's not RISC-V. Just in case you have the question. And the ISA allows compilation of 64-bit code as well. The SDK comes with a LLVM compiler, and yeah, it's publicly available. You can download it from the UPMEM website, and you can even start using it without having access to any real system because the SDK contains a functional simulator. Actually, this functional simulator, it's what we recommend to our students every time that they start working with the UPMEM architecture. First thing to do is to use the functional simulator and then go to the real system to run their experiments. And if you want to see some code, I will just show you one of the micro benchmarks that we use in our analysis. This is a micro benchmark that we use to measure the arithmetic throughput, addition of 32-bit integers. At the top, you can see the C code base, so the C-based code, and at the bottom, the compiled code. So this is the for loop. So basically, as you see, the micro benchmark, the very first thing that does is allocating a buffer. This memalloc in line 2 is simply allocating a small buffer in the WRAM, in the scratchpad memory, and because there is where we are going to place the operands that we will use later. Then in line 3, we have a for loop that goes through the entire chunk of data that we have in WRAM and reads one element from buffer A, moves it to a register, adds one value, and then stores back to the buffer A that is in WRAM, as you see. How does this compile to the UPMEM DPU ISA? Well, the for loop turns into this move instruction in line 1, where we initialize the index, and then in lines 7 and 8, you see the increment, this add instruction that increments the index, and then a jump not equal in order to go back to the beginning of the loop.
So this memalloc, when does it happen?
This memalloc, it happens whenever you need to allocate something in the WRAM, in the spreadsheet. No. The management, no. So here we are talking about, give me just 1 second because it seems that this is not charging. Yeah. I don't know if you can find, I can find a solution for this, but anyway. So, okay, there are two memories here, two memory spaces, right? One is the MRAM, the DRAM bank, that is accessible by the host. You don't need to explicitly allocate anything there because the DPUs only understand physical addresses. So the programmer just should take that into account and then place the arrays that will be later used one after the other. The allocation in the WRAM happens inside the DPU kernel. So it's going to be done by the DPU itself, by the threads running on the DPU. So that's why we have it here in this code, because this is the code that runs on the DPU, okay? So same as we allocate, we can free at some point. This buffer A in principle is allocated by, so if it's written the way it is, this buffer, so every single thread, every single tasklet, that is the name of the threads in the UPMEM terminology, every single thread is allocating its own buffer A, but they can also exchange pointers, and that can be useful in some cases.
which are not actually loading any data from your QF to something that the only good combination some data just connected
For this specific micro benchmark, yes, there is no difference. Any other question? Okay. So just give me 1 second, because indeed I don't know why my computer is not charging. I think. No,
From the other side?
no, there is no other side.
Oh, can we try switching the port? Maybe?
I don't think it's gonna work, because I think that this, let's see.
Maybe this port is problematic because it's not working.
It's not working.
Yeah, so the problem is with the port.
And we don't have VGA here, right? Because I have a VGA adapter where
No, there's
only HDMI.
But I can try and ask VGA. Maybe they have VGA.
Okay, I can continue. Maybe.
Yeah, sure.
Yes, I have 10%, 9%.
Well,
battery.
it's not good.
No, this is not ideal.
Yeah, let me try.
Okay, hopefully. For some reason, the laptop, and you know, this only has two USB-C thing, and for some reason it's not charging. Because I need to use one for the projector.
Are you sure your adapters, the power adapters working?
Let's see. Yeah, actually, if I put it in the other place, it works.
Can you run the video on other USB-C?
No.
You want to try a different adapter? You said USB-C?
Yes, it is. Yes. Yeah, we can try it. Yes. Yeah, now it's charging. Oh, great. Thank you so much. Okay, problem solved.
Excuse me. So the movement of data from NRAM to WRAM is not shown here, right?
No, it's not shown here, but I'm going to show you, I can show you, I'm going to show you code later. It's in the slides. This buffer A is in WRAM, in the scratchpad. Yes. There is no explicit memory allocation in the NRAM, in the DRAM bank. Okay, so yeah, I guess we can continue. Maybe I think I need to share my screen again. Okay, sorry for the inconvenience. So yeah, I was saying the for loop we have in line 3 at the top compiles to these 3 instructions in lines 1, 7, and 8 to reset the index, increment the index in line 7, and then in line 8 we have this jump not equal instruction, right? So we have to access, we have to go to the WRAM, bring some element and put it in a register. That's what we do with instructions in lines 3 and 4. We first calculate the address with this LSL add, and then we load word. We move, in this case, 32 bits from the MRAM to the WRAM. No, sorry, from the WRAM to a register. Next, we perform the addition, is a regular add instruction, and finally the store word. Okay, I can, well, you can see many more details about the architecture itself in our previous lectures. This is one from Spring 2022. I think I've also premiered this one recently in corresponding to this semester, and you can find many more in this paper. Because we don't have all the time to go into all the details, I'm going to show you the key takeaways of our work, of this first characterization work. The first key takeaway is that as you will see, this architecture is, because the processors are not really powerful. It's a pretty weak architecture, so it's a pretty wimpy processor. In this analysis, what we did was connecting the arithmetic throughput to the operational intensity of the workloads. And in that plot, you can see in the y-axis, the arithmetic throughput in mega operations per second. In the x-axis, you see the operational intensity that we use in the micro benchmark in operations per byte. Observe that here we have a range of values for the operational intensity, very low one over 2048, which is extremely low, because it means that we are doing only one operation every 2048 bytes that we read from the MRAM. We move from the MRAM to the WRAM. This experiment is for integer addition, 32-bit integer addition, and the operational intensity goes to up to 8. So observe as well that inside each of these dots here, there is one small number. The number corresponds to the number of threads or tasklets that we use in the pipeline for the experiment. And as you see, in the very beginning, the arithmetic throughput increases with the operational intensity, and actually the saturation point happens at a relatively low number of threads. In the very beginning, it's just 2 threads, or at some point, it starts saturating with 3 threads, and so on. This area here is what we call the memory-bound region, because the arithmetic throughput increases with the operational intensity. And here, at some point, the throughput saturates. That's what we call the compute-bound region. And one thing we observe is that the saturation happens at a number of threads equal to 11. This 11, even though it's not exactly 14, the number of pipeline stages, but is connected to it. 11 is basically the number of cycles the thread dispatcher has to wait before issuing one new instruction from the same thread. So the important observation as well here is that the throughput saturation point, that is the transition between the memory-bound region and the compute-bound region, happens at a very low value of the operational intensity. For example, for the 32-bit integer addition, the throughput saturation point is 1/4. So it's pretty low. That basically means 1 addition per 32-bit element that we fetch from memory. So that's very low throughput saturation point. And what that means basically is that this architecture is fundamentally compute bound. And because the operational intensity is so low, we expect that that's going to be the case for most real workloads that we implement and run on this architecture. And that's indeed what we observe. Some other interesting observations that come from our analysis and comparison to CPUs and GPUs. In this plot here, you can see performance comparison to CPU and GPU. We are presenting in a logarithmic scale the speed up over CPU. And as you see here, we used one Intel Xeon CPU, one NVIDIA GPU, in particular a Titan 5, and then 2 UPMEM systems, the smaller one with only 640 DPUs and the old version that where the processors ran, the DPUs ran at 267 megahertz, and a larger one with more than 2,500 DPUs running at 350 megahertz. Observe that we have divided the workloads, the benchmarks, in 2 different parts, those that we call more PIM suitable and those that are less PIM suitable. The basic criterion here to distinguish between one or the other is how they compare to CPU and GPU, how fast they are comparing, how fast the PIM system is compared to CPU and GPU. But there are interesting observations here and characteristics across these workloads that are more suitable for the HBM-PIM system. One thing we observe is that they use streaming memory accesses because that's the way to maximize the bandwidth of the DPUs, the bandwidth of moving data from the MRAM to the WRAM and vice versa. We also observe that there is no or little in these workloads, there is no or little inter-DPU synchronization. And I have some slides later to show you why this is important and why this is a characteristic that makes a workload more suitable for the PIM system, is because there is no direct communication channel between different DPUs. And the third characteristic is that there is no or little use of integer multiplication, integer division, or floating point operations. And the reason for that is that the DPUs don't support these operations natively. They support some operations for integers natively, such as addition or subtraction, but not multiplication or division. These are emulated by the runtime library. So a workload with these three characteristics, we can say that is potentially suitable for the HBM-PIM architecture. So the key takeaway or two key takeaways related to these results are the most suitable workloads for the HBM-PIM architecture use no arithmetic operations or use only simple operations. Another takeaway is that the most well-suited workloads of the HBM-PIM architecture or for the HBM-PIM architecture require little or no communication across DPUs. And as a final key takeaway, just to give you also some numbers for this comparison that we did with CPUs and GPUs, we observed that the HBM-based PIM systems outperform state-of-the-art CPUs in terms of performance by more than 23 times on the larger PIM system that we used compared to the CPU. We observed as well that the HBM-PIM system, the larger one, was outperforming the NVIDIA GPU for a majority of the benchmarks that we evaluated, in particular 10 out of 16 benchmarks. And for those which are the most PIM suitable that you have seen in the previous slide, the speed up is more than 2.5 times. And in terms of energy efficiency, one observation here was that the PIM system is more energy efficient than the CPUs or the GPUs, especially for the workloads where we also see performance improvements. All our codes are publicly available in the repository, microbenchmarks, benchmarks, and scripts. This is the PRIM benchmark suite, is the name that we gave to this suite of benchmarks. So as I said, HBM is not the only real PIM system. If we have time until 12, I will go back to the HBM system and I will give you a few guidelines on how to program this system. But before that, I want to give you an overview of other real systems. The first one, which was announced in early 2021 from Samsung, is called function in memory DRAM, or also HBM-PIM, and it's targeted at AI, machine learning, neural network, inference, especially, as you can see. It's based on HBM2 memory. What Samsung folks did was modifying some of the layers in the HBM2 stack. As you see, the layers at the bottom, and inside each of the layers, they embedded a small SIMD unit that is called PCU. Basically, they placed one of these PCUs in between two blocks, two memory banks. So here we have the PCU block for bank 0 and bank 1. Here we have another PCU block for bank 4 and bank 5. And how does it look? How is that PCU? Is something like this. It's a SIMD unit with 16 lanes that operates on 16-bit floating point. Basically, the SIMD unit is near the sense amplifiers, so it has direct access, 256 bits access from the DRAM bank, as you can see. It's interesting. Well, that's also a characteristic of the UPMEM architecture. It's compliant with unmodified JEDEC controllers. We don't have a whole lot of time to go in detail over this architecture, but I can refer you to one of our lectures. The second proposal from Samsung is called AxDIMM, or accelerator DIMM. It looks like this. Is a DIMM-based solution that they first tested for recommendation system, in particular for the SLS operator. And the basic idea, or the idea, is to place one small FPGA in the buffer of the DIMM. On the right-hand side, you can see a picture of the prototype. They compared to a baseline system, and in the AxDIMM system, they replaced two DIMMs of the conventional DRAM DIMMs. They replaced them with this AxDIMM that have the small FPGA on top of it. The good thing of this FPGA is that it's configurable. As I said, the very first example that they showed was for recommendation systems, and what they did was integrating or implementing two small accelerators, one for each DRAM rank, so that they can exploit rank level parallelism. It's a pretty simple thing, as you see, with one instruction buffer here, one decoding unit, and a command generator, which is to access memory, or use this other array to perform additions, because the SLS operator is basically doing a vector addition. And finally, this PSUM buffer, where they store intermediate results. And in this slide, you can see the execution flow. One characteristic, and I think that this is, I would say, pretty common thing in existing prototypes of these processing near memory systems, is that there is no simultaneous access from the host CPU or from the host, regardless of whether it's a CPU or a GPU, and the PIM accelerator or the PIM execution unit. So as you can see in this timeline, the very first thing that needs to happen is that the host writes the embedding tables. So if the host has to explicitly write these tables to the DRAM ranks, and then it changes the mode. To change the mode, the host modifies one memory map register here in this configuration register, and then writes instructions into the instruction buffer. And at that point, the NMP unit, or the processing element, can start decoding instructions and fetching data from the rank, performing the addition in the other, storing back, etc. In the meantime, by the way, the host keeps checking whether the computation is done or not. So it's using polling to check if computation is done or not. And that's also something common in current real systems. In the UPMEM system is like that as well. And this is a link to one lecture on AxDIMM. 1 year ago, SK Hynix announced AIM. We're going to have this talk from SK Hynix folks. The accelerator in memory architecture, similar to the Samsung HBM-PIM architecture, is targeted at machine learning and artificial intelligence, or HPC applications. And it has kind of a similar design as well. They also have these small SIMD units near the memory banks, but in this case, it's not one SIMD unit every 2 banks, it's one SIMD unit per bank. The name of this SIMD unit is called process unit, as you see. And as you can see here as well, it can execute multiply, accumulate operations, and also has a certain logic for activation functions. Here you can see another view of this GDDR6 based architecture. Near each of the DRAM banks, we have this PU, as you see, is an array of 16 multipliers, and then an other three to perform the multiply, accumulate, perform dot product operations, basically. They also have these small unit for activation functions that also makes use of a lookup table in some of the rows of the DRAM banks. I guess that we will hear many details about these this afternoon. And something that I like a lot as well is that they have this supplementary SRAM buffer of size 2 kilobytes in each of the chips that allows you to move data between different banks and allows you to also place operands there. For example, the weights of that you need in the neural network inference. This is one of the lectures that I delivered about AIM, but as I said, we have this interesting lecture this afternoon. The last one of the real world prototypes that I'm aware of at the moment is this Alibaba HBM-PIM. This one is more specialized, I could say. It's designed for recommendation systems, and it's really interesting because it uses this hybrid bonding technique to glue two different layers, two different dies. One is a DRAM layer, the other one is a logic layer. As you see here at the top, you can see the DRAM core or the DRAM layer with different banks, and at the bottom we can see the logic layer with the different types of engines for the recommendation system. Basically, they have two small accelerators. One is called the neural engine, and the other one is the match engine. They are specialized for different parts of the computation. Because this is for a recommendation system, the part that runs on the, or is supposed to run on the HBM-PIM accelerator is this coarse grain matching that runs on the match engine, and this fine grain ranking that runs on the this neural engine. This neural engine, as you can see here, it's specialized in matrix computation, looks more or less like systolic array, like a small systolic array. And this is the link to one lecture on HBM-PIM. So I'm not aware of many more companies fabricating real systems, but I know at least one more. This one is Neuroblade, is a startup from Israel. They are doing also processing in memory. I don't know many details about them. I just have a couple of slides here for your reference. They file, as far as I know, a couple of patents, and what they say in the patent is that this is a distributed processor that includes a memory array and processing array, and it's divided into processor subunits that are being associated with a plurality of discrete memory banks, and there are ways of connecting these plurality of processor subunits. Yeah, you can more or less figure out how this works. There are these processor subunits near the memory instances, and then some links that connect these processor subunits. And this is just one topology. If you take a look at the patent, you will see that many different topologies are possible. Inside the processor subunit, you can have more regular or general purpose processing elements or accelerators. And this is also a picture from their website. What apparently this is, I mean, these links, these connections between the processor subunits are apparently based on PCI Express. But yeah, as I said, I don't know much more about this. And last time I checked the website, I couldn't also find much more information. But as we see, there is a variety of real PIM architectures, and we can see that there are some differences, because even though we can say that all of these are near memory processing architectures, but we see that is the type of near memory processing is not always the same. They might be near bank, for example, UPMEM, FinDRAM, AIM, or HBM-PIM, or near chip or near rank, such as such as AxDIMM. They can have more general purpose processors or more specialized function units. That's the case of FIMDRAM, AIM, and HBM-PIM. There are different execution paradigms that they use, fine-grained multi-threading in the case of UPMEM, SIMD in the case of FIMDRAM, AIM, or AxDIMM, or the case of the systolic array that I mentioned in the Alibaba prototype, and the different operations and data types that they support natively also vary. In the case of UPMEM, it only supports integers. The case of FIMDRAM or AIM, they support floating point, typically 16-bit floating point with different representation depending on their preference. And the type of memory as well might change. DDR4, LPDDR4, HBM2, GDDR6. That also depends on the type of applications and the type of systems that they are targeting. But what is more interesting to me here is that they also have some common characteristics. So first of all, in all cases, there is a host processor, either a CPU or a GPU, that has access to a standard main memory and the PIM-enabled memory. So observe that in the system, we still have a standard main memory, and they coexist with the PIM-enabled memory. The second characteristic is that the PIM-enabled memory contains multiple processing in memory elements, or processing in memory processing elements that have high bandwidth and low latency memory access. The third characteristic is that they typically run at a few hundred megahertz and have a small number of registers and a small cache or scratchpad, or maybe not at all, a scratchpad or cache. And they typically, these processing elements typically need to communicate via the host processor. It might not be always the case, as I've shown you in the AIM prototype from SK Hynix. There is this global buffer, 2 kilobyte SRAM-based global buffer that allows you to move data between different memory banks in the same chip. But likely, if you need to move data from one chip to another chip, or from one DIMM to another DIMM, it will have to go through the host CPU. This is how one of these current real-world or state-of-the-art processing near memory systems would look like, with the standard main memory, the host processor, the PIM-enabled memory, and then inside the PIM-enabled memory, we have a memory array, memory bank, or a memory rank, and then some processing elements near it. Okay? Are there any questions so far? Yes.
And they usually won't have DLP or address translation, so always have to
Yes, that's my understanding. I think that's how it is. Mm-hmm.
You may already mentioned this, but I just want to make sure. For some of the architectures that might have been FIM DRAM, which do not have the SRAM, that is called the WRAM for UPMEM, it looks like every single access incurs the full DRAM latency. Is that right?
Every single access to the DRAM, yes, I guess so. I mean, they have registers as well, right? For example, FIMDRAM, Samsung HBM-PIM. There are, I don't have here any slides with detail about their small pipeline, but they have some registers of size 256 bits. For every time they open a row in the memory bank, they can read it and move it to this register. So
there is a little bit of buffering. That is
yes. There are registers. Actually, I think I mentioned it here. There is a small number of registers. Not in all cases there is a scratchpad or something like that, but yeah, they use registers.
The way you describe some of these approaches, it felt a bit like a cheapy to me, meaning that you have like some board memory and you have like these like fast boards around it. What, like in your opinion, what would be the real like differentiator between like GPU, including and successive memory? Like
Mhm. Yes, I think that's a great question, and actually, it's helps me to introduce the next part of the talk, because actually it's you will see that in 2 slides. I'm connecting, or I'm relating these to computing in heterogeneous systems with GPUs, and that's how it is so far. You need to explicitly copy the data from the main memory of the CPU to the PIM-enabled memory, and then start operating. So in that sense, it's very similar to computing on GPUs. That said, I don't think that this, I mean, I don't think there is any fundamental reason why this will keep being the same in the future. I think it should be possible to enable processing in memory becoming main memory. I think that that's something that we will see at some point. And that's one comment. And another comment is that I also don't think, and this is something that I always try to emphasize every time I speak about the UPMEM system, for example, I don't think that we should see these processing in memory systems as competitors of GPUs. Rather than that, I think that processing in memory is a perfect complement for CPUs or GPUs.
Is just a total question. Is the completion then at some point that each and every DIMM in your system, for example, to be one of these DIMM-enabled DIMMs, or it's a DIMM rather than you always have the separation between
that's also an excellent question, and I guess that will be a matter of preference. I would expect that memory that is compute capable will be more expensive than regular memory, and hopefully it will be up to you whether you want to spend more or less. But in principle, I believe it will be possible to have an entire system built of compute capable memory, and sometimes use it for computation, and some other times just use it for storage.
So 2 practical questions. First, to what extent the compute-enabled memory has different bandwidth and performance in terms of when using it as regular, compared to, so not using computation, but just storing data and using it as if it was the main memory.
I mean, bandwidth is the same.
Bandwidth latency,
there is no difference. You're using the regular DDR4 interface in the case of the UPMEM system, or you're using the HBM interface in the case of Samsung HBM-PIM.
But do you expect, for example, as we move forward, is that vendors of those computation memories will be able to catch up because of the progress in performance of regular DIMMs, like because apparently these are different vendors.
So you mean a different bandwidth from the host? Is that what you're?
Yeah. So what I'm saying is that tomorrow there will be, I don't know, DDR 18, and those guys will still be stuck with DDR6, right? So to what extent this is this scenario where might limit the adoption of those systems in the future.
But you mean because people like, for example, this company will keep using DDR4?
Well, because for example, they need to keep the compatibility with the previous, because they cannot advances in regular DDR.
Well, I don't think there is any reason why they could not catch up with advances on DDR technology. Right now, I mean, DDR4 is still being used, and we can consider it still state-of-the-art, and that's what UPMEM is using. HBM2 is also state-of-the-art, and that's what they are using. And from the point of view of compatibility with programs that you might have written for an old generation, I think that whatever happens internally inside the memory chip with some processing elements or compute units, that will be independent of the interface. So I don't think that there is going to be any limitation in that sense. It will be also the work of the compiler as well, right? To whatever help to keep that compatibility. Yeah, I don't think that, hopefully that won't be an issue. Thank you for the question. Okay, so if there are no more questions, I will go ahead with this part, programming a general purpose PIN system. I guess we have more or less 15 minutes until the end of this session, but I will try to cover as much as possible. As we were just saying, the UPMEM DIMMs, because this general purpose PIN system that I'm talking about is a UPMEM-based PIN system. So these UPMEM DIMMs coexist with regular DIMMs, and we can say that they follow what is called the accelerator model, where we need to explicitly move data between the main memory and the PIM-enabled memory, and then we have to explicitly launch the kernel, the function that runs on the PIM processors, in order for computation to start. And this resembles GPU computing, which is something like this. This is, in fact, one slide from one of my lectures on GPU, one of the initial lectures on GPU computing. We need to copy the input from the CPU memory to the memory of the accelerator. Then we compute in the processing in memory course, in the case of processing in memory, and then we write back the results. And that's indeed what the UPMEM patent also explains. You first need to load data to the memory banks, then the system on a chip or the CPU transmits the data processing command to the DRAM processors, then computation starts in the DRAM processors, and during that time, the CPU is polling, checking if computation finished, and at that point, the memory bank becomes again accessible to the host CPU. Yeah, and this is the system organization as you remember. So we have the system on a chip or the host CPU, and then we have the multiple memory DIMMs with the memory arrays or memory banks and the small processors, the DPUs. In order to start with something simple, the first programming example is a vector addition. By the way, over the course of this presentation, you have already seen some of these boxes, color boxes with key observations or takeaways, but there are also some programming recommendations. The numbering corresponds to the numbering in the paper. So if you see that they are not sorted, it's because I prefer to keep it that way in order for everyone to more easily connect the lecture or the slides and the paper. So how to implement a vector addition in something like the UPMEM-based PIN system? In a vector addition, as you know, we are doing the element-wise addition of two vectors A and B, and we store the result in an output vector C. The typical way of mapping this computation onto the UPMEM-based PIN system is by partitioning the arrays across DPUs. So we will assign equally sized chunks of the arrays to the different DPUs, for example, these 4 DPUs, and then inside each of the DPUs where we have threads running, and I said earlier, these threads are called tasklets, we are going to do the same, right? We partition as well that chunk of data across tasklet 0, tasklet 1, etc. And we do the same for the rest of DPUs. The necessary details to learn how to program the UPMEM-based PIN system are here in the SDK documentation. You can find a link there at the bottom. And from this SDK and also from other documents, we identified some general programming recommendations when we started our work. And I think it's pretty useful to start with them. The first of them, of these general purpose the first of these general programming recommendations is to execute on the DPUs portions of parallel code that are as long as possible. And that's something that makes sense because we need to move data between the main memory and the PIM-enabled memory, so we want to amortize that cost. The second is that we need to split the workload. We want to split the workload into independent data blocks so that the DPUs can operate independently. And that's the ideal case, such as in the vector addition, right? When we assign this chunk to one DPU, this DPU doesn't have to worry about any more data in the system. And we want to do that in order to avoid the necessary inter-DPU communication that other workloads might need. We, of course, want to use as many working DPUs in the system as possible. So if we have 2,000 DPUs in the system, let's try to use them all in order to maximize parallelism. It's true that in some cases, especially when we have inter-DPU communication, there will be a sweet spot that will be likely less than the maximum number of DPUs in the system. And then the last one is launch at least 11 tasklets per DPU. And I think I mentioned this earlier, is related to the number of pipeline stages. So first thing when we start writing our program for the UPMEM-based PIM system is to do the DPU allocation. Here, we need to reserve a number of DPUs for our program. And to do so, we use this DPU alloc API that you can see here, where we say how many DPUs we want to use, and this will give us this a DPU set identifier that we are going to later use to instantiate the DPUs. One question here is, can we allocate different DPU sets over the course of a program? And yes, we can. And we have an example next, where we also use DPU free, which is when we want to free the previously allocated set. An example is one of the benchmarks that we implemented, Needleman-Wunsch. As you may know, in Needleman-Wunsch is a dynamic programming algorithm where we are computing anti-diagonals of this dynamic programming table, and the size of the anti-diagonal varies over the course of the execution. So depending on what's the size of the anti-diagonal, we have more or less parallelism. So we are going to use more or less DPUs. And so what makes sense here is that in every iteration, we free the previously allocated set, and then we allocate the number of DPUs that we need at that point, depending on what's the size of the anti-diagonal. Now that we have the DPUs allocated, this DPU set reserved for our program, we have to load the DPU binary that is previously compiled. To do so, we use this DPU load that loads a program in all DPUs of a DPU set. It's as simple as this. We use the DPU set identifier, and then we have here the path to where the compiled DPU code is. Is it possible to launch different kernels onto different DPUs? Yes, it's possible. If your program allocates two different DPU sets, you can load different programs, different kernels onto these two DPU sets, right? Or another question could be, if the size of my entire computation is too large and I cannot fit it in the IRAM, remember that the size of the IRAM is limited, only 24 kilobytes, can I load a second kernel at some point during the execution of my program? Yes, you can do that as well.
The one kernel hold on another kernel, is that right? Meaning that you can, let's say, if you want to do like
that's a very good question. I mean, there might be ways of emulating that, right? You can have your code written in a way that you call another function as if that was another kernel. Same as it can be possible to write code for thread 0, for thread 1, and for thread 2 in order to exploit task level parallelism inside the same DPU. But no, there is not something like, for example, the dynamic parallelism that OpenCL or CUDA provide. Okay. Yeah. So next thing after we have allocated and then loaded the DPU binary is we need to copy data, right? We need to move data between the main memory and the PIM-enabled memory. This is what we call CPU to DPU transfer. And at some point when the execution on the DPUs finish, we will copy back DPU to CPU transfers. And the SDK provides 3 types of transfers: serial, parallel, and broadcast. As you see, the first one, serial CPU, DPU, or DPU CPU transfers are targeting a single DPU or a single MRAM bank, What we do is copying one buffer of certain size to one of the DPUs, one of the NRAM banks that we have in the PIM-enabled memory.
So why you not actually produce data on CPU while directly inside the PIM-enabled memory? So can you, like, if I have a CPU that just reads data, I don't know, for some computations already directly in the chip, then I don't need to move in because the same things, you know?
I agree with you that there is, I don't see any fundamental reason why this is not possible. It's not currently allowed by the SDK that you directly, there is no easy way of doing that, let's say. So, I mean, you could start. So in the current UPMEM system, you need to have these two memory spaces. I agree with you. You could copy some data to the PIM-enabled memory and then read it back using DPU to CPU transfers and compute using a small space maybe in the main memory. That's something that you could try to do, but I don't think it's something really comfortable and convenient at this point. But yeah, other than that, I don't think there is any fundamental limitation. There would be challenges for sure, and I think I don't know if we are going to have time to cover it. But the thing is, the way that data is interleaved or needs to be interleaved in these PIM chips, in these DPUs, is different from the way we normally do it in the DRAM chips. Where typically in a DRAM rank, we have 8 chips and we access 8 bits from each chip at the same time, right? But now if you think about these DPUs here, you want to access entire words, right? And these words are 32 bits or 64 bits. So in order to do so, because the memory interface is the same, in order to do so, the runtime system running on the CPU needs to transpose data, and that's done by software. And that's, by the way, I think one of the reasons as well why these transfers, for serial, you could imagine that would happen, but for parallel transfers, you cannot you normally exploit the whole DDR4 bandwidth. But yeah, that's one challenge for sure, right? And you might not want to have your data laid out in that way if you are only going to use it from the host, right? Because you prefer to maximize bandwidth. So yeah, I mean, those are challenges that exist for sure. Okay, so yeah, as you see, serial, parallel, and broadcast transfers. The difference between parallel and broadcast transfers is that broadcast transfers are transferring one single buffer to all DPUs or to all the DPUs in your DPU set. For a little bit of, well, for you to get familiar with these APIs, we have DPU copy to and DPU copy from for the serial transfers. So because the UPMEM DIMMs, the UPMEM DPUs don't understand virtual addresses, we need to use this symbolic name DPU MRAM heap pointer that gives us the start of the MRAM range that can be freely accessed by the application. And observe that here we don't allocate MRAM explicitly. So it's all responsibility, programmer's responsibility to copy the data wherever we need to copy it. We start from this DPU MRAM heap pointer name, and then there is an offset within MRAM. So for example, for our vector addition example, this line here corresponds to vector A, and this one corresponds to vector B. And that's why the offset of vector B corresponds to the size of the vector A, or the chunk of vector A that we assign to that specific DPU. Here you see the pointer to main memory, the pointer to the buffer in main memory that we are copying to the memory side, and here the transfer size. Then we have the parallel transfers. In the parallel transfers, we are targeting an entire DPU set. And what we do is first preparing the transfer and then pushing the transfer. And we have also these names or these symbolic names to identify or to determine the direction of the transfer. So here you see how we first prepare the transfer. This part corresponds to vector A, this part corresponds to vector B. So we first prepare the transfer. We indicate what's the pointer to main memory for the different DPUs. This I here identifies the DPU where we are copying the or the part of the entire input that we are going to copy to each DPU. Here we have the direction. In this case, we are copying to the DPUs, the offset within MRAM in the same way as we had in the serial transfers, and the transfer size. And then the broadcast transfers. This is DPU broadcast 2, and the syntax here is more similar to the serial transfers, where we have the pointer to main memory, the transfer size, and that's it. Can we use different types of transfers in a program? Yes, we'll have to do that. And we need to do that in some cases because parallel transfers are only supported for buffers of the same size. So if we are copying data to 4 DPUs, let's say, even though the buffers will be different, the pointers will be different, but the size of these buffers should be exactly the same. So in some cases, for example, this select operation where the output is input dependent, the size of the output might change, right? And in this case, we will need to use serial transfers. The last version of the SDK has a new feature that is called scatter-gather transfers that somehow alleviates this issue, and you could potentially merge several serial transfers together and this way exploit more bandwidth. So that's a new feature. I haven't tried myself, and I hope that it will has some benefit in terms of bandwidth exploitation on the memory channel. Okay. Why the data transfer, or why the transfers between CPU and DPUs are important? Because we need to use them for inter-DPU communication. We need to understand how fast they can be, because there is no direct communication channel between DPUs. In our study, we analyze some of these communication patterns because every time we want to move data from here to here or from here to here, we'll have to copy to the main memory and then back to the DPUs. And in our work, we also did a lot of, or some analysis on how fast are these data transfers, what's the bandwidth that we can achieve. The overall, the final takeaway here is that the DDR4 bandwidth bounds the maximum transfer bandwidth, but yeah, also depending on the specific type of transfer as well, and due to this overhead of the transposition that I mentioned earlier, we might not reach the peak bandwidth in all cases.
Any overlap computations on DPU and transfer to the same DPU?
No, that's a very good question, and that's not possible right now. The reason is that the access to the memory bank is locked either to the CPU before the kernel execution starts or to the DPUs. There is in the interface, there is a sort of multiplexer that allows you to use it from one place or the other place. Okay, so very, very quickly, and I think I will have to finish because it's already over 12, but yeah, these are some experiments. Here we changed the data transfer size from 8 bytes to 32 megabytes. These are for serial transfers, so we see how the bandwidth increases. At some point, it saturates when we increase the. This is for a single DPU when we increase the data transfer size, and this is for multiple DPUs. Here you see multiple DPUs in one rank from 1 to 64. The y-axis, as you can read, is a bandwidth. If we are using serial transfers, as expected, the bandwidth remains flat, but when we use parallel transfers, the bandwidth increases. As I said, there are overheads. Why we cannot, and those are the reason why we cannot achieve the peak DDR4 bandwidth. But yeah, the best case happens with the broadcast transfers that are the red line, and there you see that it's way closer to the 19 gigabytes per second that the DDR4 interface provides. It's more than 16 gigabytes per second. I think that we believe that the key reason for this is that it has because it's just one single buffer copy to multiple DPUs. There is more more locality in the last level cache of the CPU, and that probably helps to maximize the bandwidth. Here you have one slide for the transposition, related to this transposition library that I mentioned earlier, and here you can see the link to the micro benchmarks that we use. I think I'm going to finish in maybe 4 or 5 slides, because I guess you guys are hungry already. What to do after we have copied the data to the DPUs? We need to launch the kernel, and we have to do that explicitly. It's pretty easy. After having loaded the program as well, we just need to use this DPU launch, where we target one DPU set. And this DPU launch can be synchronous or asynchronous. And that basically means whether we want the CPU to wait, or the CPU continues doing something, and then at some point check using these status bits to check for the kernel completion. The asynchronous execution can be useful to exploit, for example, heterogeneous computation on CPU and DPU. And instead of having the DPU idle, just waiting for the CPU idle, just waiting for the DPUs to finish, we can have it running something. Now, one thing is how to pass parameters to the kernel. It's very similar to the data transfers as well. We can use here serial or parallel transfers. The only thing is that we are copying directly the input arguments to the WRAM. It's where we are going to place the arguments, and to do so in the file of our DPU code, we declare this. With this special host qualifier, we declare these input arguments or output results that we are going to move from to move the input parameters, and in some cases some results if they're relatively small. And the very last thing here is that I want to show you is the DPU kernel itself, right? As you see, this is just a vector addition. Is pretty simple code. The vector addition itself is happening inside this function here that I have in the next slide. What you can see here, because this UPMEM system uses a SPND programming model, single program, multiple data, similar to what we do in CUDA or in OpenCL. We need to have an identifier of the tasklet or the pin thread, and we need to have this is the size of the vector tile processed by a DPU. We need to have the addresses of the arrays in MRAM, array A and B, and the WRAM allocation, because remember, every chunk of data from A and B needs to first copied, needs to be first copied to the WRAM and we allocate the WRAM with this memalloc here. And then we start going through these chunks, so copying chunks of data from MRAM to WRAM using these DMA transfers. It's the first time that you see this MRAM read here, but we have MRAM read and MRAM write. So with the MRAM read, we copy from MRAM to WRAM. With the MRAM write, after having performed the vector addition in WRAM, we copy back to the MRAM. And just to finish, the vector addition looks like a vector addition for a single thread, right? So you have copied buffer A and buffer B, you have the data there, so you just need to go one by one over those elements. So I have many more slides, like 100 more slides, but of course we don't have time to go over all of them. We have lectures talking about how to program this system. The code is publicly available, and And you guys have the tutorial as well that you can access from the website. If you want to give it a try, the tutorial, there are some templates as well in the website for you to modify them and run them with either with the simulator, or today you can access the real system. Hopefully it's clear and well explained how to access the real system, because we are going to be here at, still for a few hours. If you want to come and discuss anything related to the systems that I have presented, or how to program the admin system, I will be completely available for you. So thank you very much for your attention, and see you after the lunch. consultant of the MongoDB storage engine team, and she's the recipient of Anita Board Early Career Award and of the Alfred P. Sloan Research Fellowship. So thank you very much, Sasha. I'm really excited about your talk. Please go ahead whenever you're ready.
All right, thanks for the introduction. I was just trying to set things up on Zoom here because I was muted. All right, so thank you for coming to the talk. You probably learned a lot of amazing things about PIM. And today, well, right now, I'll tell you about our experience of actually using it for some real world applications. And, I'll tell you about some of the things that worked well, but, that's the boring part, like when the speaker just comes up and like shows, oh, everything is great, right? We know that in systems, like nothing is ever always great, right? There are situations when things don't work so well. So I'll tell you about those as well when PIM doesn't work so well. And the work that you're going to hear about today was done by my students. And I also had the privilege of collaborating with lots of amazing people at UPMEM, the company who built this PIM product that we're going to talk about today. And they were really amazing at, being responsive to us and helping us when we needed technical help. So this is not new information to you, right? So there is this product from UPMEM that does processing in memory, and it's available today. And some of you will have a chance to use it in the afternoon, I hear, if there's time left. But I do want to mention a few details about an alternative solution. Well, not really an alternative solution, but another processing memory solution that Samsung was talking about, releasing commercially. And I don't know what's the status of this. I think some people had access to it, but I don't know if it's widely available. And it is very, very different from the UPMEM product. It's called function in memory, and this is pretty much what it is. So it's targeted at HBM, high bandwidth memory, which is denser and more expensive memory. Sorry, it's less dense and it's more expensive. So you can't have like huge amounts of it in the system, and essentially you execute like a tiny code snippets in this memory, and there is a limited instruction set. So and you have to write an assembly. So it's a more limited programming model. And the convenience of UPMEM is that we have a general purpose programming model. We can write applications in C. So you probably saw a bunch of these pictures, and you have had an overview of what how UPMEM hardware works. But I'm going to perhaps repeat some of these details again, because I want to emphasize a few things that will be relevant for today's talk. So we'll just repeat a few things. So basically, it's the chip that looks just like regular DRAM, but inside is different. So we have the DRAM processing unit, the GPU, that's the processor that does the work. It's simple in order. It runs somewhere between like these clock speeds to 500 megahertz. Now, in practice, it runs at about 350 megahertz. It's harder to run it at a higher clock rate because they have to supply more power to memory. And usually the power comes from the motherboard, and the motherboard just does not currently have enough power to supply to run the memory at 500 megahertz. And they can supply the power. They have this setup in this lab where they kind of plug in extra wires to memory, and sorry, to the motherboard to supply this extra power. And they can even, like, if you're purchasing hardware from them, they can even like send you this kit with extra wires and tell you how to use it. But you know, it's not something that you could just like drop in you know, into the data center. If you want to just like put the chips into the regular commercial server, then at this point it will run at about 350-ish megahertz. So there's one DPU per 64 megabyte slice of RAM. So if we have an 8 gig DIMM, we have like 128 of them. And so that's actually also an important number, 8 gigabytes. So if you try to purchase DRAM, like regular DRAM these days, you'll see density of up to, you know, 64 gigabytes. And with UPMEM hardware, you know, because we're adding extra stuff to this DIMM, we're adding processors, there's less space. So far, I have not, you know, heard about them increasing the density, right? So that's going to be one of the limiting factors. Now, what's going to be important for next few slides is that each DPU, each of the DRAM processing units, has its own DMA engine. And so what this means, so each DPU has its own DRAM slice of 64 megabytes, and it would just read the data like from that slice and only from that slice and not from any other slices. And of course, that's going to be an important limitation. We're going to talk about this later. But the advantage of this architecture is that the GPU has its own DMA engine to memory. So if we have a bunch of DPUs that are accessing memory through their own DMA engine, we don't have any of the memory bandwidth limitations that we usually see with the CPU, right? We don't have this memory wall phenomenon because, you know, what happens with the CPU, you have a bunch of CPUs, they're very powerful, they're able to ingest and process data at a high rate, but then they all go to memory through this like single memory controller or a couple, maybe like a 4 memory controllers if you have a very expensive system. And, you know, it's like they're just not able to supply data quickly enough. And here we don't have this limitation. And so that's going to be one of the superpowers of this architecture. So here is and here's the experiment that demonstrates the potential of what we can do. This is a very simple experiment, and it's not anything that, you know, a real application would do, but it's kind of the best situation that we can set up for this memory. So the best that we can do. And so the y-axis shows the throughput in gigabytes per second, so higher is better. The x-axis shows the amount of memory we're using in gigabytes, so up to 32. And, you know, the more memory we're using, the more DPUs we can use, because with each 64 megabyte slice, there is a DPU. So as memory scales, you know, the number of processing elements also scales. And so the experiment is very simple. We just, so we have an array of data, and we just go through every single byte and we'll look at it, like, you know, add them up or something, right? So very simple. And we do this with UPMEM memory. So the computing is done like inside the memory in DPUs. And so the blue line, or if you can see the colors, like the one that goes across and up, that's PIM, that's processing in memory. As we add more memory, we get more compute power, we get more bandwidth. So it just goes up, and it will keep going up as we add more memory, because we're adding more memory, we're also adding more bandwidth. Okay. Now with if we're doing the same computation on the CPU, we are limited by how many memory channels we have. So the lowest line here, the red line, if you can see it, is going to be the where we have only one memory channel. So we're going to be limited by about, you know, 19 gigabytes per second with DDR4. And then, you know, if we have like a super duper expensive system and we have more memory, like 4 memory channels, then we're just going to multiply this by 4 and we're going to be limited by, you know, by that bottleneck. So that's like a very simple and clear illustration of, you know, CPU hitting the memory wall and the GPUs are not hitting the memory wall. You know, they just keep going. In reality, of course, the question is, you know, okay, how well can we realize this potential for real applications? And of course, like there are probably very few applications where we can just like get all of that, right? But so we'll talk about nuance a bit later. There is another aspect I want to talk about because I don't think it gets talked a lot, is the total cost of ownership. So let's look at, you know, if you're actually buying this memory and, you know, versus using regular memory, how much does it cost you? Now, I have to tell you is that, so we're using the numbers based on, you know, current price of UPMEM memory per DIMM. And of course, you know, the prices are, you know, very fungible. Like if they had like a huge, you know, volume, the price would be lower. And another thing that we're not considering in these calculations is that the density of UPMEM DIMMs is a lot smaller than that of a regular DRAM. So there's, you know, we can just put less of this memory into the machine. So, but, you know, given these two caveats, here is the story that I can tell you. So what we're going to have is the following. I'll show you the process type, because on CPU, if you want to put more, you know, more memory into the system, you need like a higher end processor. And we're going to be populating our system with some DRAM and possibly some PIM. Like we'll look at several scenarios, and we'll show the maximum achievable memory bandwidth that we can have with this hardware and the costs in dollars, you know, given this number. So if we have a low bandwidth system, so, you know, we have something that, you know, doesn't really need lots of memory bandwidth. And if we have a system without PIM memory at all, you know, we can get like up to maybe 100-ish, 100 plus gigabytes per second in our system. And, you know, if we add a little bit of PIM memory, you know, only 24 gigabytes, like really not much, then, you know, we'll get like some extra memory bandwidth there, but our cost is going to double, right? So, you know, if you want to have just a little bit of PIM in your system and, you know, bandwidth is your limiting factor, probably that's not going to be advantageous. Like the low bandwidth capacity is not going to be advantageous for you. Now, if we have a medium bandwidth system, now we're going to look at this picture a bit differently just to understand it better. So let's say you have a budget of about like, you know, 6.5 K. How much bandwidth can you buy with either of, you know, of these memories? And we can see that if we have, you know, a little bit of DRAM and a lot of PIM memory, you know, because when we get this PIM memory, we're not just buying memory, we're also getting like more DMA engines that can be accessed directly by this processes, right? So we're buying more bandwidth essentially, right? With the CPU, we can buy more DRAM, but we're not, if we're keeping, like, if we're not upgrading the class of CPU, we're not getting more expensive CPU, and we still keep the one memory channel, we're still going to be limited by this, you know, 19 gigabytes per second per memory channel, like no matter what we do, right? So if I want to have like upgrade and get a high-end, you know, Intel system, so I'm going to have extra memory channels, then I can get like up to like a terabyte bandwidth, but the CPU system is going to cost me like, you know, an exorbitant amount of money, right? More than 80K. All right, so I promised you that I'll talk to you about applications. Okay, so let's talk about applications. So these are some power numbers, but we'll skip that for now. So this, so first I'm going to show you the good news, right? And then we're going to get more into nuance. So this application is something that works, that actually behaves like pretty closely to what I just showed you on the previous slide. So this is hyperdimensional computing. So you have these hyperdimensional vectors, like basically very large vectors of, dimensions of, I don't know, 10,000. And we're just, so what we're doing at the level of access is we're just like reading these vectors and doing very simple operations on them, like, element-wise summation or something. And so this hyperdimensional computing is used in various, AI-ish things like, gesture recognition, for example. The model is encoded as this hyperdimensional vectors, and then to do inference, to query the model, we have to do some simple computations on these vectors. But mostly, what we have to do is basically like traverse a large amount of data. And so you see, so this is just the speed up relative to doing the same operation on the CPU. So the flat line is the CPU, and we can see that with PIM, so doing the operations on GPU, as the amount of data increases, and we're not even talking about large amounts of data here, because this is such a good application for this. With like only 3 megabytes of data and 512 GPUs, we see like a very substantial speed up relative to doing this on the CPU. And so the beauty of this is that we just park our data on GPUs in GPU memory, and then the GPUs do all this data shoveling inside, and then they return like a tiny result back to the CPU. Okay, so the data doesn't have to cross this barrier, this memory channel, and so that's a really good scenario. Now this is a bit different. This is compression, and again, this is throughput relative to a single CPU. On the y-axis, so high is better. We have file size on the x-axis, and as we increase the amount of data, we're using more memory for processing this data. And on the top here, we see the number of GPUs that we're using for that. And we're comparing to doing the same compression just on a whole CPU. So here, so these results are end-to-end in the sense that we have the file that is, so we read it from disk, so it's sitting in host memory. We copy it over to the GPU memory, and I'll explain why a bit later why we need to copy this data, right? Why the data is not just like is not imported into the GPU memory in the first place. So we'll talk about this later. So anyway, the data sits in the regular sort of legacy DRAM in CPU memory, and then we copy it over to the GPU memory. We perform the compression, and then we copy the compressed result back. Okay, and so we see that. So these are the curves, and we want these curves to go, up very high as we increase the data size, as we increase the number of processing elements. And some curves are doing really well, like, and these are different files, and some curves are doing, less well. They don't scale as well. So the difference is in compressibility. If the file is very compressible, then we get back, so we copy the file, and then we have to copy back the result. The file becomes very small, so we have to copy back like a small amount of data. And if the file is not very compressible, let's say that we have, some kind of encrypted file, so like we can't really compress it. So if we copied like 1 megabyte, we have to copy 1 megabyte back. So we basically have to copy a bunch of data back and forth. And when we copy the data back and forth, we go through this memory wall bottleneck, which is the memory channel, and that would limit our performance. Okay, so I'll drive this point home a bit more with the next couple of slides, but just to remember this takeaway for now, because I think this is the main takeaway that I'd like you to have during this talk, is that so DPUs are there potentially to address the memory wall, right? This bottleneck. But if the way we're using the GPUs requires us to, to stress this memory channel, then, what's the point, right? We're hitting this memory wall somewhere else.
Is it a multi-core CPU, like you're using all the cores?
No, it's a multi-core, but we're using just one core now.
But how can you use all the channels then with the single core?
We have only one memory channel on the system.
Oh, so the comparison is with a single memory channel.
Yeah. So if we used more than one core, this curve would be higher. Yeah, it would be, sorry, it would be a bit higher. So I'll show you results later where we use like more CPUs. Yeah, and in this experiment we use more CPUs. So so this is image processing. Don't try to read the chart yet. I'll explain to you what it is. So first, the motivation was that, when we're training image recognition model, we're pre-processing a bunch of images. So, they're in JPEG, we have to, decode them, and then we might have to scale them and all of this. So this is, so we thought, okay, maybe, and it was shown to be a bottleneck in some training workloads. So because of this pre-processing, you can't drive the GPUs as fast as they can take the data. And so our motivation was, maybe we can do this pre-processing on GPU memory. And so so what this workload does is that, there is a bunch of images sitting in legacy DRAM. We copy them to the GPU memory, we decode them, to JPEG decoding, and then we copy them back, right? And so this is the time. So this is latency. So lower is better to decode a certain number of images. So the number of images is shown on the x-axis, like from 64 to 1K. And with DPUs, as we increase the number of images, we increase the number of DPUs that we use. Okay, and so this the yellow bar where the arrows are pointing, that's PIM, that's our processing memory, and the comparisons are to do the same thing on the GPU, which is the second bar, the green bar, or doing this on a CPU with varying numbers of CPUs, like 1, 2, and 1, 3, and 6 CPUs. And so what we can see here is that, so if you ignore the bar where we're doing, just one CPU, which is, not a very good configuration here, like, doing this on GPUs or on a multi-core CPU, like DPUs don't really have a big advantage here, okay? And so the difference, so the reason for that is that when we are decoding images, we're just moving data back and forth all the time. So here's the breakdown of what happens in our workload when we're running it on a GPU. So this red part at the bottom is the useful work. You can ignore the blue part of the bar at the bottom here, because this is the GPU setup, and we in a real application we can just set them up once and like not repeat it every time. So like this we can easily eliminate. So the red part is the useful work, is when we're decoding the image on the GPU, and you can see that like the height of red bars, it stays unchanged, because as we add the number of images, we add more DPUs, right? So we get more bandwidth, more computational power. But what you can see here is that as we add more images, like this yellow and blue part increases, and that is because we just have to copy more data back and forth. Okay, and so basically we are we're using this bandwidth and computational capacity of memory during decoding, but for us to prepare for the encoding, like to get the data that we need, we go through this memory channel, and and essentially it limits our performance. Now, why can't we just, why do we have to copy data between, GPU memory and CPU memory? Why can't we just treat it as, this is our memory, and, we use it as, like, CPU uses this memory whenever it needs, and then GPUs compute it whenever we can. Like, why? Like, that will be the holy grail, right? So unfortunately, there's one important limitation, and it's not something that can be overcome very easily, because so I'll tell you about what the limitation is in a second, but maybe I'll start with that so it's easier to understand what I'm talking about. So we have a bunch of GPUs, and each GPU talks to its own DRAM slides via its dedicated DMA engine, okay? And there are no wires across, like, going from one GPU to another. Like, pairs of GPUs are actually connected, but it's it's not the case that there is a wire from any one GPU to any other GPU, right? It's just not there. And UPMEM chose to not, like, that they could have done it, with some sacrifices, but they chose not to do this for various reasons, and mainly they wanted this DIMM modules to be like a drop-in replacement for existing regular DDR4 DRAM. So they didn't do that, and so the GPUs cannot talk to each other. Now, when the CPU accesses DRAM, the CPU, let's say the CPU has to write a cache line to DRAM. So it takes the cache line and it splits it across multiple slices, okay? And when it reads the data back, when it reads that same cache line back, it reads across multiple DRAM slices in parallel. And that is done, to improve the parallelism when you read and write, and to decrease latency. And like, this is like such a normal thing to do in systems. I mean, like enterprise level SSDs work this way. They just, split your data across multiple dies. So it's like a very normal thing to do, right? But what happens is that if the CPU writes the data this way, the GPU will not see like the whole data structure. It will see, some number of bytes of this data structure, but not the whole data structure. And that makes it really hard to write algorithms, right? If we think in terms of data structures and processing these data structures, but now if our algorithm has to work on like every 8th byte of the data structure, that makes it kind of really, really tricky to think about it. So what happens is that, the UPMEM library deinterleaves the data. So it kind of copies it in a way that all the data structures land into the DRAM slices sequentially, okay? But what this means is that, so this is a simplified picture of how the interleaving works. In reality, it's more complicated. So they had to turn off, hack the BIOS to turn off interleaving at one level, and then they use the library on the CPU to, to make sure the data lands in the right format to offset the other type of interleaving. Okay, but if you didn't like, if that sounded like too complicated, that's totally fine. It's really difficult to sort of digest this and explain and talk. What's important to remember is that if we want both the CPU and the GPU to access the data, we can't keep it in like just, the format that makes both happy, okay? So that's why, when we want the GPUs to do some computing, we usually, get the data, let's say from file, so the CPU issues a read, and then DMA, whatever the data lands in legacy DRAM, and then to get GPUs to compute, we have to do all this like deinterleaving and and transposition and copy it into that memory, and then copy the result back. Okay. And so I showed you what happens when we don't have to copy a lot of data. So remember that hyperdimensional computing where we saw nice scaling, because we copy the data there once in the beginning, and then we just like do a bunch of processing on it and return a tiny result back. Like, so that's a good situation. And then I showed you what happened with image processing, where for each new image, we copy the data back, and we copy the data to GPU memory, and then we have to copy it back. And then again, back and forth, then we don't see such good performance. So, and that's our key in understanding. So, what are the applications where this may work, okay? And one application that we're exploring currently is so deep learning recommendation models, so doing those in PIM. So DLRM it's very popular model to use these days, and it's for recommending what movies to watch on Netflix, or deciding like what is the next thing to show you in your Facebook feed. So that kind of very, very important for businesses, as you can imagine, very widely used. And so those models have two parts. It's like a computationally intensive part and also a memory bandwidth intensive part. So those models decoded as those very large and sparse matrices. And so to do the inference, to ask the model, hey, what's the next thing for me to do? You have to basically like go through a bunch of rows in this matrix and do some kind of aggregation, like do row-wise addition and return back the result. So the without getting into detail about how these models really work, you have to process a large amount of data, but what you really care about is like one small result, right? And that's perfect, right? So that's exactly what we want for our PIM hardware, because we can put that data is called embedding tables. We can just put them, once we have the model, we don't retrain it very often. So we can just park the model in PIM memory. And whenever we do the inference, we just ask it, hey, do the inference. So we send it like a small amount of information that tells us exactly which rows we need to access. And then we get back like a small result. Okay, so there is still some data copying back and forth, but not a tremendous amount. We don't have to like copy the entire model there and then back. So we're not quite done with this research. This is like in progress, but here are some preliminary results. So we have an embedding table of 4 gigs, and we're splitting it across GPUs. So we have like about only 2 megabytes of data per GPU. So that's not a lot of data. We're going to see, and we have seen better results when we have like more data per GPU. But like I said, it's in progress. My students probably running experiments right now, so it's still coming up. Now, the chart shows the inference latency. Okay, so lower numbers are better, and inference is like when we query the model, right, to give us the result. So lower numbers are better. The x-axis shows the batch size. The batch size is how many queries we have per inference. So as we increase the batch size, we're just asking the hardware to do more work per single inference cycle, okay? And so there are a couple things to note here. Well, I mean, the first exciting thing is that the latency of when we're asking GPUs to do the work is like much lower. And this is end-to-end. This is like integrated into PyTorch, and this is it's a synthetic workload. We're still working on the actual ones. the more realistic ones, but it's like the model that Facebook released for others to experiment with. So it's like pretty close to the real thing, right? And it's end to end with all the Python and its overheads and such, right? So we can see that the latency with GPUs is much lower than with the CPU, and also notice the difference in the strands, right? So with GPUs, as we increase the batch size, so we're asking the hardware to do more work per inference cycle, we're increasing the latency, right? I mean, you have to do more work, right? So it takes longer. But with the CPU, we kind of have, we don't have this well-defined trend. And the reason is that the CPU is able to do these computations super quickly, but CPU is subject to another bottleneck. And the bottlenecks, so that's why, you give it more work to do, doesn't really matter, but the memory-related bottlenecks are so large that they kind of dominate this latency. So let's look at where the time goes. So that's the breakdown. So the arrows are pointing, so this yellow bar in between, that's the useful work. That's the useful work that we're doing on GPUs. And so the other bars are when we copy the query to GPUs and from GPUs. So the copy time looks pretty large relative to the time that we spend doing the actual work. And that is because, like I said, in this experiment, the amount of data that we have per GPU is tiny. So when we scale up the experiments, this yellow part is going to increase, okay? Now, this chart is more telling of what's happening. So this yellow bars show the IPC on the CPU when we're doing inference on the CPU, okay? So no GPUs involved, we're doing all the inference on CPU. You see that the IPC is tiny. So CPU is struggling to keep the processor busy. It's, waiting on something, okay? And this is, multi-core version. We're using, we compiled PyTorch with OpenMP to use all the cores and whatnot. So, we're giving the system the parallelism as much as we can. Now, but the IPC, so the other two bars, so the first, the blue bar, is the IPC of GPUs, and these are very simple processors. They can at most do like one instruction per cycle, and you can see that they achieve one instruction per cycle, and it means that we are pretty efficient at using the DMA engine. So the GPUs that have also multiple task plots, they're not waiting on on memory copies at all. So they just fully utilizing the memory bandwidth that they need. And we can also see that the CPU, when we're using the GPUs, the CPU is also involved. Like it's splitting the workload among GPUs, it's getting the results back, and it's doing some aggregation of the results. So the CPU is very, very efficient here because it's not bottlenecked on memory anymore. So the CPU, the IPC of the CPU, when it is sharing the work with GPUs, is also quite high. It's more than one because it's like an out of order CPU. We also clearly see that the CPU implementation hits the memory wall. Now, this is the hit rate of L1 cache and L2 cache, or last level cache, when we do the inference on the CPU, right? So CPU is doing the work. So you can see that the LLC hit rate, and LLC is the last frontier before we have to go to main memory, it's like only 25%. So we're not, we're really not doing well. We're waiting on memory. But when we do the work on the GPUs, so this is we're doing the work on the GPUs, but we're measuring the cache hit rate on the CPU because GPUs don't have caches. And I already showed you that the DMA engine and the scratchpad are used efficiently. We're not waiting on memory. I just showed you in the previous slide. So now we're asking, okay, when the GPU is doing some of the work, what is happening with the hardware utilization on the CPU? And we can see that it's pretty good. Like our LLC hit rate is like 3 times higher, up to 75%. And our L1 hit rate is also not bad. Okay. And I have no idea what time it is, but I'm pretty sure I'm running out of time. So I'm quickly going to show you one more application that we're working on that we think will be promising for GPUs. And this is even more work in progress. So I'm not going to talk too much about it, but Nilu, who's doing the work, is right here. So if you have questions, you can talk to her. And I'm fortunate that I can relay all the questions to her. Okay, so here's another application that we're thinking. So this is a very common scenario of how certain companies. So this example is motivated by Meta. Facebook, back when they were publishing those papers, they have database servers, they have application servers that need to get data from those databases. But if you just let application servers access the database servers directly, then it's going to be a huge bottleneck. So what they do is they put a layer of caching servers in between, and these are in-memory caches of keys and values. And so the hope is that in most cases, applications will just get the data from this cache, and we won't have to go to those database servers that have to do like more heavy lifting to get the data. And so the question we wanted to ask is, well, can we run those cache servers like in memory? So sort of like memcached that runs completely on PIM, okay? And we were like potentially sort of, moonshot ideas. We were thinking of completely getting rid of CPUs in those systems. So if you can have, NICs that support RDMA, and you can just like send RDMA request for, your get to this server that only has those memory blades, and, we don't need a CPU there at all. And then we can build more effective system where we can, we don't need to use so much space, on the motherboard for CPU, and then we don't need to use power for CPU, and we can just like put more memory that can self-compute, right? And so what we found out earlier in this work, well, what Nilu found out is that if you just do like gets and puts, it's not very effective, because the values that you get back are, not very large, right? But then you have to send the request, and you have to get the data back. Even if you batch, you get requests, still you end up doing, lots of copying. So you're subject to that data copying bottleneck that I told you about. We want to avoid, right? But what we're thinking about now is to do like a more high-level operations, like filtering, like aggregation, things like that. So if you can imagine like a column store architecture, like key value store with column store architecture, you just split the columns across GPUs, and then you tell it you can filter or aggregate, and the GPU just sweeps through this column very, very, very quickly and returns like a tiny result back to the CPU, okay? And the preliminary results are very, very promising. So this is a simple filtering operations on the CPU, and if we do them on the CPU or using a small number of GPUs, these are these curves at the bottom that you can't even see, and this is a relative speed up, and I assume it's relative to one CPU with 8 cores, right? But if we use more GPUs, then with 640 we see already gigantic speed up, and with 25K GPUs, it's like, you know, really enormous. Okay, so this is not yet integrated with, you know, with a database. This is a micro benchmark, but you know, if the starting point is that promising, we're that, you know, the end-to-end solution will have some benefit to it. How am I doing on time? Okay, I'm just, I sense that the audience is kind of losing focus already and falling asleep. So I'm just going to, I'm going to switch to, yeah, I'm just going to spend maybe 2 or 3 slides on kind of big, crazy idea that we don't know if it'll ever come to fruition, and then I'll wrap up. So, you know how recently we're seeing 2 trends. One is disaggregation, you know, disaggregated storage. We had that for decades. Disaggregated memory, right? So we want to put storage, you know, further away from the CPU. Now we want to put memory further away from the CPU because it's, you know, it can save costs, easier to administer, and all of that. And then we also see the opposing trend where the memory and compute are blending, like with PIM and you know, and experiments where people use processors that are inside SSD to do actually to run parts of the application, right? So these trends, they seem to be opposing, but you know, my hypothesis is that we can use them together to actually help one another. So let's say we want to have disaggregated memory, and it has you know, various problems. I mean, we see so many papers on disaggregated memory, and because you know, in principle we think it's a nice idea, but to make it practical we have to solve all these challenges, right? So can PIM help us? So what if we could build our disaggregated memory from this, you know, PIM enabled DIMMs? And you know, of course, there are practical challenges. Like what I emphasized in the beginning is that the density of UPMEM DIMMs currently is only 8 gigs, right? So it's a lot smaller than, you know, 64 gigabyte densities that we see with DRAM, and you know, maybe even higher. So there are some practical barriers even to this idea, but you know, we're in research, so we can at least explore and, you know, dream about things. So if we could build disaggregated memory out of PIM-enabled DIMMs, what could we do? One simple idea is a memory allocator. So there are questions if we build a disaggregated memory system. You know, how do we manage memory? Is there, you know, a centralized server, or is there like a P2P management system, right? So and if we're compressing memory in a disaggregated system, then management becomes even more complicated, because we need to now slice the memory in uneven chunks, right? Because if we take a 4K page and we compress it, then, you know, we don't know what size it's going to be. So one idea that we explored is to use those UPMEM and, you know, UPMEM DIMMs to compress remote memory. Okay, and Siper here, who's sitting next to Neil, he tried to do this work. So if you want to talk to him about how that went, you can. I'm not going to talk about this more. So another idea is going even further. So the like one of the most challenging issues with adopting disaggregated memory is that it is because of latency. So if we have local DRAM, the access time is, 100 nanoseconds. If we have bandwidth contention, it would go to 1,000. But if we're going across the network and we're doing, all the right things and using all the right hardware and bypassing the kernel and yada, 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 the best number I've seen is 10 microseconds. So it's like accessing SSD. So, but if we ditch the CPU's load and store interface to access memory, and if we use our memory, our disaggregated memory to run applications or parts of applications, then we can do much better, and we can maybe deploy disaggregated memory much sooner. Okay. And basically our reasoning for exploring what applications can run successfully on PIM and how to, probably it's very difficult to make the entire application run there, but more realistically, deciding what work gets done on the CPU and what work gets done in memory, so that those ideas were to answer this big question, how can we build these disaggregated systems more efficiently? Okay, and I'm going to stop here. Sorry, I don't have a slide that says right. Yes.
So you have shown very good results when you're targeting single op. What is, based on your experience, what are the challenges or ways, opportunities that you want to do this kind of work for the entire application, for the whole application, or the whole data? What would be the complications?
Sharing. It's really hard to build a system where there's no sharing at all. I mean, we read, of course, about, databases where, we do very little sharing, we split the data structures, but, there's still a little bit of setup that you need to do. And then it's just, there are no wires going between CPUs. It's just very difficult. And, how do you orchestrate that? So what does it tell us about maybe future implementations of processing in memory? Maybe we need to address this trade-off by adding those wires and, enabling developers to use them at their discretion, at least sometimes, right? So that challenge, and also GPU processors are pretty wimpy. So if you have floating point, you have to work around that, which is what we did with DLRM. And sometimes there are just certain things that just CPUs are so much better at, where, these processors, they're like Niagara processors, they're, if you're doing something very, very simple, they could, and embarrassingly parallel, they could handle that, but in other cases, they would just be much, much slower. And, if you want to make them more sophisticated, then you're using more space on the DIMM and you have lower density, and then all of that becomes not commercially viable. So maybe figuring out which fast operations it's important to do close to memory and building, ASICs for those pieces. So, yeah.
So very interesting results, and I concur completely about the potential of PIM. Otherwise, I would not be sitting here. However, looking at some of the graphs you showed, where you said it's only using a single memory channel. When I look at modern processors like the AMD Genoas, these are really cheap in terms of server processors. Just $3,000, you get 12 memory channels on chip. Over 450 gigabytes per second of memory bandwidth. of one chip, and you can really load up the machine with 128 gigabytes DIMMs if you want to. So I am under the impression, correct me if I'm overly pessimistic here, that while the longer term potential gains of PIM are still to be harvested, especially when newer generations of truly PIM capable processing elements come up that also have higher memory density since the gigabytes that happen currently. Short term, I find it's probably going to be very difficult to compete with that multi-server cluster machine with this AMD gamma engines.
Yeah, no, I agree with you. I think that short term it will only be able to compete if we find this, killer app that just happens to do really well and, with not very expensive setup. And you mentioned AMD. We haven't looked at AMD, costs. I mean, Intel, like everybody knows, is more expensive than AMD, and we just looked at, because you can only use this DIMMs with Intel machines. So we only looked at, okay, if we had to go with Intel, what would we have, right? But I mean, there are other architectures. There was like ARM, of course, and So yeah, no, I agree with you that that presently to make this commercially viable, it would require a killer app and some big company that depends on this killer app and like really wants to have the volume. Yeah.
So, small question. So, this is all on AxDIMM. That's right. So this AxDIMM device. Then what are the sort of fundamental things that you think will be, across different architectures of those memory devices, and what are very specific to that app? So what your conclusions do you think you can generalize?
Yeah. So I think the great thing is that we can have a processing element that can access a small slice of memory at very high bandwidth. I think this is very powerful, right? Very powerful. But then we also see that, because they tried so hard to make it very easy to deploy commercially, right? So they said, okay, we're just going to go with, we're just going to make it DR4 compliable, right? And the DIMM is going to look like a regular DIMM and be limited in terms of power, and this is where it becomes hard to address the limitations. So, like obviously, interleaving is there. We have to address it, and then the difficulty at clocking at a higher rate, right, is also because of that, and the lack of communication is because because we have to comply with that. With the physical and protocol design limitations. So I think that ultimately going forward, if we wanted to start from a clean sheet, we would need to keep this superpower of processing element directly accessing memory and sitting next to memory, but change our external constraints and APIs to address those other limitations.
I have a question in the economics part of I wonder which part of it you uploaded to, and for example, you should upload the training phase for inference. And also which other part you uploaded, I wonder if it involved any floating point operations or not.
Yeah, so the question was, if anybody is watching on Zoom, for DLRM, just some specifics, which part we were doing on PIM, was it training on inference, and what did we do with floating point operations? So it was only inference. So traditionally training is done only on GPUs. but it's more economical to do inference on CPUs because GPUs are better utilized for other things that they do best. So it's very common to do inference for DLRM setup on CPUs. In companies who run large data centers and dedicate pretty significant amount of resources to doing DLRM inference. And so DLRM inference has two parts, which is very compute intensive and which is memory bandwidth intensive, which is when we look up those embedding tables that are, pretty large matrices and, sparsely populated, and we do like a regular access across them. So there are floating point operations involved by default, and we used quantization that was done by others for other reasons, and that showed that basically it's fine to use that. It does not affect accuracy too much. So we just used what others found previously to convert to integers. But when we present the results back to CPU, we have to convert them back to floating points. So there is a little bit of that pre and post processing happening there as well.
Got it. So you use quantization to change that only to integer, right? Gotcha.
Yeah.
Yeah.
If you want details, you'll have to talk to my student. Yeah, and I can connect you if you need to.
I wonder if the throughput scales in
Sorry?
If the throughput scales with the number of GPUs in PIM.
The question is if the throughput scales with the number of GPUs in PIM. Yes, it absolutely does, because each GPU does additional computation, it has additional memory, and then it has an additional DMA engine. So if we keep the amount of data constant and then we spread it across more GPUs, then we just have, extra computational capacity and, extra bandwidth. That's one way to scale. Another way to scale is to just make a problem larger and just use more GPUs, for as long as we can. And then if the copy overhead is not so much, then we're just doing more work, but we're not taking more time because we have, this extra hardware. Yeah.
Comparing other platforms, because, for example, when you see people keeping the point, for example, like endpoints, that it has more throughput compared with the existing PIM. Existing PIMs, then increasing the number of units at some point.
So that's a very good point. So the question was, it makes so I'll take a liberty of rephrasing what you said, that it's kind of weird to compare with CPUs and GPUs, for example, because if we use GPUs, we can increase the workload, and if we increase the data, if we increase the data size, if we increase the amount of memory that we use, we also get like extra compute with it, right? Or we get extra memory bandwidth with it, right? But with the CPUs, if we're already using, all 16 cores in our system, and we increase the amount of data, we use more memory, we don't get extra compute. But, that's exactly the point of this architecture, because, compute is tied to memory. So yeah, it's weird, but that's what it is. Yeah. So I think so. Juan is standing up, so I think I should wrap up. I'll be at the conference, so find me, and I'm happy to answer questions.
Really nice.
But before that, I want to very briefly frame the stage for him, and then we can go with his talk. I think this can be quick, hopefully, because Professor Mutlu already introduced the thing in the morning, processing using memory. I will very briefly. Oh, so, for him. Oh, now it's me. Just one of me. Okay, so yeah, as I was saying, I'm going to very briefly set the stage for our next speaker, who is Ataberk Olgun, a PhD student in our group. He's going to talk about a processing using memory framework, or an end-to-end framework for processing using memory, where we have explored some of these analog operational properties of memory components, and how it's possible to use these kind of properties in real systems. Seems that I'm sharing the presenter view with Zoom. There are always issues with this. Okay, hopefully it's fine now. Well, anyway, as I said, in the morning, Professor Mutlu introduced this idea of processing using memory, like, for example, activating multiple rows of DRAM at the same time in order to perform some computation. This is one of the trends in processing in memory. As you remember, we talked in the morning about processing near memory. Now it's time to talk about processing using memory. And in particular, we are going to focus on DRAM, which is where, well, several people in our group are doing research. So as I said earlier, processing using memory exploit the analog operational properties of the memory circuitry to perform computation. This exploit the internal connectivity to either move data or perform computation, and leverages the large internal bandwidth and parallelism. And a common approach in these processing using memory architectures is to perform both bitwise operations such as AND, OR, XOR, etc., that we can later use to implement more complex operations. As you may remember, the way that DRAM operates is pretty simple. We have a storage capacitor and an access transistor, and whenever we want to access data, we raise the word line, the capacitor starts sharing its charge with the bit line, and then we enable the sense amplifier that amplifies the deviation of the bit line, and this makes that the charge of the capacitor is restored, and the sense amplifier has either zeros or ones that we can read from outside. So by making use of this way of using memory, or by this DRAM operation, it's possible to perform some interesting operations, such as, for example, bulk data copy and initialization. And this is one work that Professor Mutlu introduced in the morning, the bulk data copy that avoids all this data movement between memory and the CPU every time that we want to copy, for example, one entire page of 4 kilobytes to another place in memory. With something like row clone, with this in-memory copy technique, is possible to directly copy from one memory row to another memory row. So that's the basic idea, that reduces bandwidth utilization, and it's a low latency and saves a lot of unwanted data movement. This is the basic idea. We activate one row, then we transfer the row to the row buffer. Next, we activate the destination row, and this way we perform the copy. And this is something that can be done with as little as 2 consecutive activations. After that, some students in our group realized that it was possible to also make use of these analog operation and perform bulk bitwise operations, right? And so here the idea is to just activate multiple rows at the same time, and this way perform or do majority functions, majority operations. Imagine that we have 3 rows, A, B, and C. Now we are focusing on a single bit line. We activate the 3 rows at the same time. If that was possible in a real chip, we activate the 3 rows at the same time, and this makes that the capacitors start leaking their charge with the bit line. When we activate the sense amplifier, what's going to happen is that the sense amplifier is going to amplify the whatever charge represents the majority. So if we have 2 1s and 1 0 in the DRAM cells, the result is going to be 1. If we have 1 1 and 2 zeros, the result is going to be 0. So that's what is called the AMBIT technique. And using this AMBIT technique, which is basically a majority function, is possible to implement either AND or OR. And if you have AND and OR, you are very close to being functionally complete. And what that means is you can implement more complex operations. And that's indeed what the authors of this paper, the AMBIT paper, proposed for the first time. In later work, SIMDRAM, what we did was exploiting that to implement more complex operations. It's a SIMDRAM framework for processing using DRAM that basically takes advantage of the majority functions inside DRAM and performs bit serial computation with a vertical data layout, and also it's a majority-based computation. So instead of using AND, OR, and NOT, it uses majority and NOT, which is basically more efficient on this substrate because majority is what in reality is being supported by the DRAM, by the AMBIT technique, or this idea of the triple row activation. So I prefer to, I'm going to make all these slides available to you in our tutorial website, so you can take a look by yourselves. There are also multiple, several talks and lectures about these techniques in our website, in our courses, and you can take a look by yourselves. But I think that at this point, I prefer Ataberk to take over and explain us and gives us a good introduction to the end-to-end framework for processing using memory that uses real DRAM chips and shows pretty nicely what's the strong potential that these techniques have. So Ataberk, you're ready?
I am ready. We never tested this out, but can you hear me and see me?
We can hear you. We can hear you very well.
Okay. So can you now see my slides?
Not yet. Okay. Well, I can see them.
Okay.
To switch. Give me 1 second.
Yeah.
Okay, we can see them now.
Okay, cool. I'll get started immediately in the interest of time. Is that fine?
Yes, please. Go
ahead. So yeah, I'll present PyDRAM, an FPGA-based framework for end-to-end evaluation of processing in DRAM techniques. I'll start with the executive summary. Commodity DRAM-based PIM techniques improve the performance and energy efficiency of computing systems at no additional DRAM hardware cost. However, there are challenges in integrating these PIM techniques into real systems, and these are not yet solved. And we cannot use general-purpose computing systems, special-purpose testing platforms, and system simulators today to efficiently study system integration challenges of commodity DRAM-based PIM techniques. And our goal is to design and implement a flexible framework that can be used to solve system integration challenges and analyze the trade-offs of end-to-end implementations of commodity DRAM-based PIM techniques. And our key idea is to develop an FPGA-based framework that allows us to achieve our goals. And we evaluate this framework using end-to-end integration of 2 PIM techniques on an FPGA prototype of the infrastructure we developed. In our first case study, we study row clone operations that allow us to copy data in row granularity in DRAM. And we observe 119 times speed up for copy operations compared to CPU copy when we include system support. It takes us 98 lines of Verilog and 565 lines of C++ code over PyDRAM's code base to implement this case study. And in our second case study, we implemented DRAM-based to random number generator. And we observe that we can generate two random numbers with 8.3 megabits per second throughput and only at 220 nanoseconds latency. And it takes us 190 lines of Verilog and 78 lines of C++ code over PyDRAM's code base to implement this case study. PyDRAM is fully, freely available as an open source on this link that you see down below. So this is the outline for my talk, and I'll quickly introduce commodity DRAM-based PIM techniques. These techniques use operational principles of memory to perform both data movement or computation inside memory chips. And commodity DRAM chips today can already perform a subset of operations that we talked about today. The first example is row copy operations, which allows us to copy data, bulk data in row granularity to random number generation, implement physical unclonable functions, and implement the majority operation. I'll focus on the first two because these are the most relevant operational primitives to our talk. So I'll start by introducing the key idea of row clone, maybe again. Here is a simplified diagram of a DRAM subarray, and we would like to copy data from the source, orange source row to the destination row. We will do this in two steps. We will first copy the data from the source row to the sense amplifiers, and then we will move the data back from sense amplifiers to the destination row. The first step is something we can already achieve in commodity DRAM chips by simply sending an activate command. And to implement the second step, we will violate DRAM timing parameters. So our key idea in implementing row clone in real DRAM chips is to use what we call carefully crafted DRAM command sequences. We use an activate, precharge, activate command sequence with greatly reduced DRAM timing parameters, as was done in compute DRAM and prior work that demonstrated in-DRAM copy operations in real DDR3 chips to implement row clone. So I'll describe this very briefly over a simple diagram where we use standard DRAM timings and send an activate, precharge, and activate command. What will happen is we will first activate the row S. That is the target of the first activate command. Then precharge the DRAM back and then activate row D. So these will happen sequentially, and the DRAM device will operate like as it does normally. When we violate the DRAM timings and pull the commands together, what will happen is as if the DRAM chip will ignore the precharge command, and this will allow us to move data from row S to row D. So I'll describe this over a different figure, different view. So this is a simplified diagram of two cells on the same bit line. And the top rectangle shows us the voltage of the bit line, and the other two rectangles show us the voltage levels of the cells. So first we send an activate command at time 1, and then we send a precharge command after a while. And by the time we send the precharge command, the data in row 1 has already been copied essentially to the bit line. So the bit line and the cell has the same voltage level. When we activate row 2, after we send the precharge command, the bit line will start to go down to VDD over 2. But before it completes that operation, we activate the second row, and this will allow charge to flow from the bit line to the second row we activated. Essentially, by violating DRAM timing parameters, we have copied data from row 1 to row 2 in this diagram. And for more details and more operations, I refer you to the compute DRAM paper, where you can find detailed explanations on how they implement the majority function in the real DDR3 chip, and more details on their characterization study done on real DDR3 chips. I'll continue by introducing a key idea of our in-DRAM two random number generator. Here is another simplified diagram of a DRAM subarray, and here we color and size the cells according to their failure probabilities when we access them with a reduced access latency. So the red or smaller cells have higher chance of failure when we access them with a reduced latency, and green cells have a low chance of failure when we access them with a reduced access latency. The key idea of D-range is to really find cells that have a close to 50% chance of failure when we access them with reduced latency. And then we will sample these cells consecutively to generate random bit streams. We can implement commodity DRAM chips already support, in a sense, DRAM operations, because we can already violate DRAM timing parameters and access DRAM cells with reduced access latencies today. We have learned today that PIM techniques can help us improve the performance, energy efficiency of our systems, and sometimes even enhance security. But how do we provide system support for PIM? So here I will try to describe that system support over an example. We will try to implement a bulk data initialization application, and we want to back this up with row clone functionality in the DRAM chip. So how do we bridge this gap? We likely need some support for custom timing parameters at the microarchitecture level, some support to control some sort of control logic for PIM operations. And we need a software interface to execute PIM operations that will communicate with this control logic. And finally, we need some supervisor software that will provide the basic system support for us to be able to, for example, allocate data that satisfies the requirements of row clone operations. PyDRAM bridges this gap with customizable hardware and software components. And doing so, it allows users to rapidly implement PIM techniques and solve the system integration challenges and analyze the end-to-end implementations of these PIM techniques on real FPGA prototypes. PyDRAM is composed of 4 key components. On the hardware side, we have support for controlling PIM operations, a memory controller that supports custom timing parameters. Now, on the software side, we have an interface for applications to make use of the PIM capability, and a supervisor software that provides basic system support. We attach these key components to a real system to build PyDRAM's full system design. Here we use the Rocket chip, RISC-V Rocket chip, that includes a simple RISC-V CPU core and a real DDR3 DRAM module in an FPGA prototype. So next, I'll continue by explaining the key components one by one. So we'll start with the PIM operations controller. The components is responsible for decoding and executing PyDRAM instructions, such as the ones we will implement to perform in-DRAM copy operations. It receives instructions over a memory mapped interface from the RISC-V CPU core, and it has a simple interface to the PyDRAM memory controller, where it sends a request and then waits until the request completes and then reads back the results. The PyDRAM memory controller performs PIM operations by violating DRAM timing parameters, and it supports conventional memory operations and implements one state machine at the hardware description level per such operation. And this allows PyDRAM's developers to easily replicate a state machine to implement a new operation. And the physical interface controls the physical DDR3 interface. It receives commands from the command scheduler and operates the DDR3 pins. On the software side, PIMolib, or PIM operations library, contains customizable functions that interface with the PIM operations controller, and it provides the software interface for performing PIM operations. An example function in this library will execute load and store requests to communicate with the PIM operations controller. Finally, the custom supervisor software exposes PIM operations to the user application via system calls, and it also contains the necessary OS primitives for users to be able to develop end-to-end PIM techniques, such as memory management and allocation for specialized for row clone operations. I'll describe how PyDRAM works over an example execution flow. Here, the user calls the copy function to perform a row clone copy operation inside the DRAM chip. The application will first make a system call to with such semantics. The user intends to copy n bytes of data from array A to array B. The custom supervisor software will call the corresponding PIMolib function and supply the following arguments. This S points to the source DRAM row's physical address, and D is the destination DRAM row's physical address. The copy function will execute 2 store instructions in the CPU. The first store will update the instruction register with the instruction that will perform the copy operation. The second store sets the start flag in the flag register, and this essentially initiates the PIM operation. Then the PIM operations controller instructs the memory controller to perform row clone, and it resets the start flag so that a new instruction can be executed. And it will set the acknowledge flag, indicating that the execution of the last issued PIM operation has started. And the PyDRAM memory controller will issue DRAM commands with violating DRAM timing parameters to perform the row clone operation. And when it's done, it will set the finished flag. Meanwhile, the copy library function will periodically check either the acknowledge or the finished flags based on a user supplied argument using load instructions. And when the checked flag is set, it will return. We didn't use the data register in this example because the results of row clone operations are essentially stored in memory. However, we will use it in the DRAM TRNG use case. So to summarize, these 4 key components orchestrate PIM operation execution in PyDRAM's real FPGA prototypes. And this is what our prototype looks like. And this is a Xilinx DC706 board. We prototyped the full system I described on this board that includes the RISC-V system and what we call a PIM-enabled DIMM. It's a commodity memory module from Micron. So I'll continue by describing our case studies. I'll start with row clone. This is just to remind you that we violate DRAM timing parameters to implement row clone operations. For that, we extend the PyDRAM memory controller to support the DRAM command sequence that we will execute. And we expose this operation to PIMolib by implementing the copy function in the library. And this will take only 198 lines of Verilog code. We then identify 2 challenges in implementing row clone end-to-end. First one is memory allocation, and it stems from the intra-subarray operation of row clone. And the second one is memory coherency, which happens due to us computing on data that resides in DRAM. So to solve the second problem, we implement the CL flush instruction in the RISC-V CPU, which evicts a cache block from the CPU caches to the DRAM module. And we use these instructions prior to row clone operations to ensure that the data we're operating on in DRAM is up to date and it doesn't have updated cached copies in the CPU caches. Now I'll describe the first challenge in more detail. So we identify memory allocation requirements of row clone operations, and I'll describe them over this figure. On the x-axis, essentially, we have 2 banks, and on the y-axis, we have 2 different subarrays. The first requirement is the granularity requirement, which states that operands must occupy their rows completely. The second requirement is alignment. Operands must be placed at the same offset due to how row clone will copy data from one DRAM cell to another DRAM cell that reside in the same bit line. Finally, the third requirement is mapping, which says that operands must be placed in the same subarray because we cannot copy data using row clone operations from one subarray to another subarray. An example allocation, the fourth allocation here, satisfies all 3 requirements, and this is what we would like to have. To ensure that we can allocate data in the way that I showed you, we implement a new memory allocation function. The goal of this function is to allocate virtual memory pages that are mapped to the same DRAM subarray and that are aligned with each other. So this is the semantics of that function we implement. It takes 2 parameters, the size of the number of bytes that we would like to allocate, and the ID essentially is used by the user to ensure different allocations are placed in the same DRAM subarray. I will describe how this works over a very brief example. So we have the subarray mapping table, which is a core component, that core data structure that this function uses. And the allocaline function called by the user to allocate 4 kilobytes of memory will first get a physical address pointing to a DRAM row in subarray 0 indicated by the user by accessing the subarray mapping table. And then it will update the page table to map the virtual address to subarray 0. And then it will return this virtual address to the user. For details on how this allocation mechanism works, I refer you to our paper. and I'll continue by describing how we evaluate this use case. So this shows the summary of our system configuration. We evaluate two micro benchmarks. The CPU copy micro benchmark uses load store instructions to copy data, and the row clone copy uses in DRAM copy operations with and without CL flush to copy data inside DRAM. We also execute two copy initialization heavy workloads, forkbench and compile. And finally, we also evaluate one workload from the spec 2006 with a libquantum where we replace call lock with in DRAM initialization operations. Finally, the 8 kilobyte row size in our DRAM chips or DRAM module determines the in DRAM copy initialization granularity we use. So this plot shows the throughput improvement we have when we use in DRAM copy and initialization over CPU and copy initialization for different array sizes on the x-axis. We observe that in DRAM copy and initialization can improve throughput by 119 times and 89 times respectively. However, this does not include the overhead of CL flush operations. Here we assume that data in DRAM is up to date and there are no clean or dirty cached copies residing in the CPU's caches. Then we evaluate the overhead of CL flush operations. This plot shows the same on the y-axis, and on the x-axis, we show how the fraction of the proportion of data that's dirty that resides in the CPU caches. And here we assume an array size of 8 megabytes. So the leftmost bar essentially shows the case where the 8 megabytes resides in DRAM and the CPU caches. We have to evict this data that resides in CPU caches prior to the row clone operation, but this data is not dirty, so it does not have to be written back to DRAM, but we still have to execute CL flush operations. And the rightmost bar shows the case when all the data is dirty, meaning that we have to execute CL flush operations, and these will be written back to DRAM. We conclude that CL flush dramatically reduces the potential throughput improvement that row clone operations can help us obtain. Finally, I'll quickly summarize the results we have for other workloads, starting with forkbench, which is a copy-heavy workload. Here on the left y-axis, we show the speed up that we gain by using in DRAM row clone operations. And on the y-axis, the amount of time different configurations of the fork benchmark spends on mem copy operations. And the number after the hyphen indicates how many pages are copied by this fork benchmark after we execute one fork call. So we observe that performance improvement increases as the amount of pages that are copied by the fork call increases. And for compile, we observe a 9% execution time reduction when we use in DRAM initialization compared to CPU initialization. And we attribute this reduction to the fact that compile spends only 17% of its execution time on initialization. Finally, for spec 2006 libquantum, we observe 1.3% end-to-end execution time reduction. And we also observe that libquantum spends only 2.3% of its time on initialization. I'll continue and then conclude by describing our second case study. So this is just to remind you that we want to find cells that fail with 50% probability when we access them with reduced access latency. To implement this, we identify 4 DRAM cells that fail randomly in one cache block in DRAM, and we continuously sample this cell to generate our random bit streams. This is what we exactly do, and then we need to reduce the access latency, and we store these random numbers in a 1 kilobyte buffer in the PIM operations controller. And finally, we allow users to read these random numbers by implementing the rand-DRAM function call in the PIMolib. And it takes us 190 lines of Verilog and 74 lines of C++ code over PyDRAM's existing code base to implement this study. Finally, to evaluate this, we develop a micro benchmark that just reads two random numbers by calling the rand DRAM function. And here we show the throughput we obtain on the y-axis, through random number generation throughput we obtain, depending on the random number generation period that we can configure in our prototype. We observe that PyDRAM's implementation of D-range can generate two random numbers up to 8.3 megabits per second. I'll conclude with an executive summary. So commodity DRAM-based PIM techniques improves the performance and energy efficiency of our systems with no additional DRAM hardware cost. However, there are challenges of integrating these techniques, and we cannot study these integration challenges on existing platforms. And our goal is to design and implement a new flexible framework that developers can use to solve these system integration challenges of commodity DRAM-based PIM techniques. And we develop an FPGA-based framework, and we evaluate this framework using two case studies. The first one on row clone, where we observe 119 times speed up for copy operations. And the second case study we do is D-range, where we obtain 8.3 megabits per second through random number generation throughput. PyDRAM is fully open source at this link. There is an extended version of our TACO publication on archive, and you can find it at this link. And there's a longer talk that includes a tutorial on how to use PyDRAM on YouTube at this link. Thank you for listening to me, and I'd like to take questions if there are any now.
Thank you very much, Ataberk. Do you guys have any questions for Ataberk?
Just please let me wear my headphones real quick so I can hear the questions. And then.
Hello, Dan here. Maybe I don't think you really addressed.
Okay, maybe I cannot.
Possible.
Now I can hear you.
For future research, but how, as we push DRAM in particular faster and faster, it obviously comes to more error cases, and we have to increase refresh, etc. And at the data center level, we're concerned about things like STC.
I'm so sorry, I cannot really follow because I cannot hear you well. If Juan could ask me the question.
Repeat the question.
Okay, so I'll just jot out my question. And how do you handle or implement ECC?
Did you hear, Ataberk?
No, I couldn't hear it well, sorry.
So the question is, how do you handle or implement ECC in this kind of system?
Yeah, so that's a good question. I think one thing you could do is, once you have a DRAM module that has extra capacity, like additional chips to store the ECC bits, you essentially need to modify our memory controller slightly to implement an ECC engine where you operate on, well, basically where you encode and decode the data that you write and read from DRAM. This shouldn't be too difficult, I think, in our prototype. And the row clone case study, I think, is synergistic with this sort of ECC implementations, because when you copy the data, assuming that it's completely correctly copied, you will essentially copy the ECC bits as well of the data in the source row. And then you have the error correction bits of like in the destination as well. So that doesn't necessarily mess with the ECC you have. For true random number generation, maybe the ECC is not as relevant, because there you're trying to really your goal is not to really be reliable there. You're trying to find cells that fail with 50% probabilities. So you're looking for cells that fail essentially. For other primitives like the majority operation. I think it's a maybe someone can update me on this, but I think it's kind of like an open research problem on how to implement efficient ECC techniques, because there the operation really modifies the values you have on multiple rows, and you have to manipulate the ECC bits in a way that the result of that operation will have the correct ECC bits that you would get by encoding the result of the operation, which is not, I think, which is not something you can do by just performing a majority operation today. But going back to, I guess, how you would implement it, I guess the answer I gave in the first part should be okay, I guess.
Okay, yeah, thank you very much, Ataberk.
Okay, we're out of time.
Yeah, I think there are no other questions, so yeah,
Cool.
Thank you again.
Thank you. Goodbye.
Okay, yeah, I think we can continue in about 10 minutes for the remaining two talks. So I hope to see you here after the coffee break. And after that, I want to show you as well some slides of our work or experience with real-world workloads, implementing them on the HBM-PIM architecture. In total, I guess I will take about 20 minutes, and then we will have the invited lecture, the invited talk with SK Hynix folks. This is something that Professor Mutlu already mentioned in the morning. The adoption issues, different issues that still need to be solved in order to enable the integration of processing in memory capabilities in real systems. And these issues are, you know, a variety. There are a variety of them. We need to figure out what are good applications that are suitable for processing in memory systems, as well as developing software that is appropriate for these real-world processing in memory systems. And that's the second presentation, the second set of slides that I'm going to show you now. How to deal with programming these systems, how programming needs to change, what are interfaces and compiler and hardware support. There are also different issues related to integration in the system, such as coherence, synchronization, virtual memory, and also security, isolation, for example. What happens when we want to have different applications running their workload or running parts of the workload in PIM systems? It's a problem that, by the way, the HBM system doesn't have. It's not. I mean, it's not possible to run two processes at the same time on the same DPU. What HBM recommends is to just allocate a set of DPUs, and these DPUs will be used independently by the different applications. We also need runtime and compilation systems that can do adaptive scheduling, data mapping, or access and sharing control. And of course, infrastructures to assess the benefits and the feasibility of processing in memory solutions. And this means simulation frameworks or end-to-end frameworks, such as the one that Ataberk Olgun just presented, or processing in memory benchmarks as well. So all of these can be solved step by step with a change of mindset. And this is something that spans the entire stack, from the problem and the algorithm to the devices. And we can go there step by step. There is some, you know, for more details about all these different topics, I recommend you to take a look at these at the book chapter that Professor Mutlu mentioned this morning. We have an entire section, section 8, where we discuss all these different issues and also present some of the works that are already trying to solve all these different issues. But I will also link from the website an entire lecture that covers this complete presentation, which is pretty long. We have more than 150 slides here that obviously we are not going to cover now, but if you are interested, you can watch the lecture offline. So right now, what I'm going to do is switching to the other presentation that I have, because I really want to show you a little bit about our experience with programming the HBM system and yeah, how this HBM system can. Let me 1 second. How this system can be useful for different real workloads, which I think is also going to be a good complement to what Professor Fedorova showed us earlier. Just change the PowerPoint in the middle of the talk is probably not a good idea. for some reason, it's not shown now. Okay, I will put it here, and I think we'll be fine. And now I can share the screen. So as I was saying, this is a presentation that I will also upload to the course website, and I think it can be useful for you as well to understand what's the potential of this processing in memory system, the first general purpose processing in memory system for accelerating modern workloads. It's basically the first point in the enabling PIM lecture that I showed you earlier, and I think it can be a good way of wrapping up our presentations about the UPMEM-PIM system. The first thing that I want to show you is the benchmarking and workload suitability study that we did as part of our first analysis for first paper on the UPMEM-PIM architecture, and this suite of benchmarks that are called PRIM, processing in memory benchmarks, that have the typical goals of a benchmark suite, evaluating a specific architecture, in this case the UPMEM-PIM architecture, compare software improvements and compilers, compare also future PIM architectures and hardware. And we tried these workloads to be, that represent an interesting variety of workloads from different application domains, and also workloads that are potentially suitable at least for a processing in memory system, because they are shown to be memory-bound workloads on processor-centric architectures like CPUs and GPUs. In total, we have 14 different workloads and 16 different benchmarks, because there are 2 different implementations for 2 of the workloads. The applications domains, as you can see, are also very diverse: density linear algebra, sparse linear algebra, databases, data analytics, graph processing, neural networks, etc. And as I said, the first thing that we did was observing that all these different workloads are memory bound. These are results of the roofline model on a CPU, on an Intel Xeon CPU, and as you see, all the 14 workloads fall in the memory bound area of the roofline. The workloads are as well diverse in terms of memory access patterns, sequential, strided, random access patterns, operations and data types, and also in terms of synchronization and communication needs. Some of them need intra-DPU communication or inter-DPU communication, and some of them don't. And regarding the communication, there are also different ways of inter-DPU communication, like, for example, merging results that have been merging of results on the CPU, results that have been partial results calculated on the memory side, or redistribution of intermediate results, for example, in BFS or in Needleman-Wunsch, where we have to go back to the CPU, maybe perform some computation on the CPU, and then offload again to the memory side. All the benchmarks are available in our repository, including the scripts and the data sets. So if you are interested, you can take a look. I'm going to very briefly show you some evaluation results. They correspond to a strong and weak scaling experiments on the UPMEM-PIM systems, this system with more than 2,500 DPUs, and also we also have here the comparison to CPU and GPU, but I think that I can skip those results, that comparison, because I mentioned in the talk in the morning. So the strong and weak scaling experiments, as I said, first of all, we evaluate the scaling on a single DPU for different number of tasklets or PIM threads. Then a strong and weak scaling analysis on one rank, which are 64 DPUs, and then evaluation, strong scaling analysis on up to 32 ranks. And as I said, the comparison to the CPU as well. This is the UPMEM-based PIM system that we use for our evaluation. Remember that is a dual socket CPU that has some DIMMs of regular DDR4 memory that behave or operate as the main memory, and then 20 DIMMs of PIM-enabled memory or 20 UPMEM DIMMs. So in total is up to 2,560 DPUs and 160 gigabytes of memory, which in some sense represents an advantage with respect to other accelerators that usually don't have such large memory. In our work, we also use a smaller system with 640 DPUs. These are the data sets that we use for strong and weak scaling. Some of them are synthetic data sets, but others are real data sets. And yeah, you can check the details in this slide and also in the paper. Let me very briefly introduce some of the results. These are the strong scaling results on one DPU. As you can see here in the plot for the 16, well, these are for the 16 benchmarks, but let me show you the results for vector addition, for example, so that you can see the breakdown of the execution time. Observe that in the x-axis, we have the number of tasklets per DPU. In the y-axis, we have the execution time. And here we are showing the execution time on the DPU kernel time, the inter-DPU communication time, which is not the case when you have a single DPU, of course, but for the a larger number of DPUs, we have inter-DPU communication in some cases. CPU to DPU time, which is when we move the data from the main memory to the PIM-enabled memory, and finally DPU to CPU time when we move the results back to the main memory, and also the speed up over one tasklet. Some observations, some observations that we can see here is that for most of the workloads, we see that the best performing number of tasklets is 16. Observe that here we are testing 1, 2, 4, 8, and 16 tasklets. We know that the performance in most of cases saturates at 11 tasklets, but that's why, because we are not testing 11 or 12, that's why we see that we see here that the best performing number of tasklets is 16. And the speed up is also as expected. We are pretty close to doubling the performance when we double the number of tasklets from 1 to 8. After that, from 8 to 16, the speed up is not 2 times because performance saturates at 11 tasklets. Please.
I'm wondering about the inter-DPU category. Some of the benchmarks like reduction, UNI, and SEL did indicate they require inter-DPU communication. But when I look at the bar charts, maybe my glasses are too, I don't see something in the inter-DPU color, or is it really so short?
No, it's just that the legend is wrong here, because there is no inter-DPU communication when you have a single DPU. But don't worry, because I have results for 1 rank and for up to 32 ranks. I'm going to show them to you. Anyway, before we go into that, also the effect of synchronization, intra-DPU synchronization. In some cases, it's lightweight. In some other cases, it's not that lightweight. For example, BFS, one of the versions of the histogram and the transposition workload use mutexes, and this causes contention. For example, this is for one of the versions of the histogram where we see that the best number of tasklets is not 16, is 8 in this case, but that's due to the overhead of the mutexes. I'm going to skip these. You can check them later. And I want to show you the results, the strong scaling results on 1 rank. Here, in this case, you can see inter-DPU synchronization needs. For example, in BFS, which is iterative, and after every single iteration, we have to move the frontier or partial frontiers from the different DPUs back to the host. The host aggregates them and then redistributes the work over the DPUs in the system. And as we could expect, because all communication happens through the host, as we increase the number of DPUs that we are using, the overhead of the inter-DPU communication gets significantly increased. Observe that, for example, for BFS, 64 DPUs, even though the kernel time reduces significantly, but the overhead of the inter-DPU communication makes that it's preferred to use 16 DPUs rather than 64. If we check the total execution time. So yeah, these are also results for Needleman-Wunsch. It happens something similar here. There is a significant amount of the inter-DPU communication that definitely burdens the overall performance. Yeah, I don't have a whole bunch of time, so I will very quickly go to some other results that I want to show you here in this presentation. We also have slides about our analysis of sparse matrix vector multiplication. We have a sparse matrix vector multiplication, one implementation of a sparse matrix vector multiplication in the PRIM benchmark suite that corresponds to the first study, but after that, we also perform a much more detailed analysis of this important primitive sparse matrix vector multiplication with up to 25 different implementations that use different compression formats for the input matrix, different, as you can see here, different partitioning techniques, 1D, 2D partitioning, load balance across threads, synchronization approaches, etc. More recently, we have also worked on machine learning training, not neural networks, because that's not, or dense neural networks, deep learning, because that's not expected to work well on this architecture. One of the key reasons for that is that it doesn't support floating point computation natively, but we observed that it can be pretty promising for some workloads. For example, here, as you can see, decision tree and k-means. These are results, scaling results for decision tree and k-means. Let me go to the comparison to CPU and GPU. Here we observe a speed up of 25 times for the decision tree over the CPU, a multi-thread implementation on CPU, and also 34% faster than the GPU version that runs on an A100 GPU, which is a really powerful GPU with 1.5 terabytes per second. In these experiments, we are including the cost of moving data from the main memory to the memory of the accelerator in both cases. And because the UPMEM DIMMs are connected to the memory channel, the aggregated bandwidth is higher than the bandwidth of the PCI Express for the GPU. And for k-means, as you see, we can also see about something between 2 times and 3 times faster than the CPU implementation and the GPU implementation. I'm going to finish in a couple of minutes just to show you a few more results. These ones correspond to a more recent work that it's already publicly in archive, publicly available in archive, but it will be also published in the Bioinformatics Journal. It got recently accepted. Is an implementation of the wavefront algorithm. The wavefront algorithm is a state-of-the-art algorithm for sequence alignment, and we have shown that is also very promising thing here. The implementation is embarrassingly parallel because it targets short reads. So basically, we are moving a bunch of short reads or read pairs from the CPU memory to the DPUs, and then performing all these alignment. The individual tasklets are doing the alignment on different or multiple read pairs, and yeah. So if here you can see some results comparing the implementation on the PIM system to a multi-thread implementation of up to 56 threads. You observe that it's a really powerful server, but still it cannot perform well because at some point, well, very quickly with 16 or 32 threads, already the throughput saturates due to the bandwidth limit, and at the same time, in the case of the PIM system, we see an interesting performance improvement. This is logarithmic scale, so it doesn't look so large here, the speed up, but it's like more than 4 times, as you can see, faster than the implementation with 56 CPU threads. And if we don't include the data transfers, it's even larger, right? It's up to 37.4 times. And by the way, this is a workload that could really it doesn't really have any inter-DPU synchronization. It's embarrassingly parallel. We just move the read pairs to the memory side and then compute. So if the PIM-enabled memory becomes main memory, eventually that happens, we can see these high speedups for such an important workload. And that's basically what I wanted to show you. I'm pretty sure that we will have future lectures about this work in more detail, because the work that is going to appear in bioinformatics also implements other genome sequence alignment algorithms, and I think it will be a pretty interesting thing. And there is indeed more to come. Another work that will appear soon is this one, library for transcendental functions on processing in memory systems. That it's something that we also needed. We also had to do, because transcendental functions are not functions that can be natively supported by any sort of hardware, especially when you have something as weak and wimpy as the UPMEM DPUs. And the paper, as you will see, hopefully after we presented in ISPA's 2023, we have observed some interesting improvements compared to running the transcendental functions on the CPU. So that's all for now. Now I think it's time to hand over to hello, Jonky. How are you?
Can you hear me?
Yes, we can hear you. I think we can hear you pretty well here in the room.
That's great.
Just 1 second. The stage will be yours.
Oh yeah, can you give us a permission to screen sharing?
Yes, I'm going to do that right away. Okay, you should be able to share your screen now.
Okay, let me try. All right, no idea. Do you see the entire screen or presenter mode?
I think we are seeing the presenter view right now.
Okay. How about this?
Yeah, now it looks good.
Okay. Okay, let's get started. So thank you, Onur and Juan, for the invitation. This is great honor and pleasure to talk about SK Hynix's accelerator in memory, or AIM for short, on the behalf of many others who contribute this work. So I'm Yongki Kwon, PIM project lead from SK Hynix, and I will be joined by my colleague Chan Park, PIM software team lead. So this slide shows the graphical summary of today's talk, which is largely based on our last year Hachis poster. As shown, give me a sec. Accelerator in memory is a processing in memory specialized for memory-intensive machine learning applications. So today we will focus mainly on AIM software system for the sake of interest of ASPLOS attendees. So please refer to the references at the end of this talk for more information about circuit level details or hardware aspect. So I will first briefly go over AIM architecture with our design goals, and followed by AIM system that is designed to exploit AIM's full potential. Then Chanuk will take over and talk about AIM software stack and performance analysis using AIM FPGA platform shown at the bottom, right the corner. Everything's going okay?
I think it's going okay. I was just trying to see if I can raise the volume, but seems like that's its maximum. So, but yeah, we can hear you.
Okay, I will speak up then. So before diving into the details, let me begin by talking about domain-specific accelerators. You know, as AIM can be considered as an accelerator, as the name stands for. So I took this article, you know, about domain-specific hardware accelerator, appeared in Communications of the ACM 2020 by Bill Daly and two others. So it's shown the domain-specific accelerator is a hardware computing engine that is specialized for particular domains of applications. As shown in the head message, the DSAs, you know, gain efficiency from the specializations and performance from parallelisms. So such accelerators can offer orders of magnitude improvement in either performance per dollar or performance per watt compared to general purpose computers. In this sense, AIM can also be considered as a domain-specific memory, unlike UPMEM, probably you learned today. The domain in which AIM is specialized for is a set of DNA applications that are bounded by memory bandwidth. So I'm going to explain the key target operations in the next slide in more detail. The main goals and how AIM achieves them are as follows. First, AIM achieves high performance by exploiting high degrees of parallelism available inside DRAM. Also, AIM as a processing in memory can save significant power by avoiding majority of data movement between a host and AIM. Last but not least, one of the important design goals was to minimize the cost. Again, one of the common goals for domain-specific accelerators as well. Therefore, by the design time, we opted for commodity DRAMs over high-end memories such as HBM or high bandwidth memory. Furthermore, we choose GDDR6 for our first generation, and GDDR6 offers the highest bandwidth among available commodity DRAMs. And because of that, we projected GDDR6 became popular for AI inference accelerator, which is our primary use case. So the key kernel that AIM is accelerating in memory is matrix vector product. It's shown at the top right corner here. So for matrix vector product, the entire matrix is read just once, making it bound by memory bandwidth. So note that matrix vector product is a key kernel for many DNA applications. So in fact, the operation, you know, like shown here at the top, precisely describe the end-to-end fully connected layer. There are many DNA algorithms that are dominated by the execution times of fully connected layer, and GPT is one of such examples. So the figure at the center shows AIM over architecture. First of all, it's shown GDDR6 is composed of 16 DRAM banks. And each bank is associated with its own processing unit, as shown here. So to exploit the maximum degrees of parallelism as discussed. So as you can see, the way matrix is okay. So as you can see, these weights are all like scattered across all 16 banks. On the other hand, the activation vector is now stored in the global shared buffer, one unique data structure we added in accelerator in memory, and then it now gets broadcasted to the multiple MAC units, as shown here. Let's now zoom in the MAC units as shown in the top left. So given the two vectors of 16 floating numbers, one from the bank, another from the global buffer, MAC units performs multiplies and accumulate operations using a set of multipliers shown here, followed by reduction at tree, and stores the final reduced floating numbers in the special register at the bottom shown here. Moreover, AIM also implements activation function module following MAC register. It's because it's quite common in DNA applications. It's also denoted as F here. The simple function like ReLU is supported at the circuit level. Otherwise, we use lookup table to compute arbitrarily, potentially complicated functions such as GALU with linear interpolation for better accuracy. Excuse me. The table summarizes the key features for GDDR6A. It's shown in the die photo at the bottom right, shown here colored blue. Each bank is associated with its own processing unit to fully utilize the internal bandwidth again. So the bottom line is that our accelerator in memory achieves high performance without compromising available band parallelism, like any DSA would do so. So as a result, AIM achieves 1 teraflops at peak, which is 16 times higher than external bandwidth of 16.4 gigabyte, which host can utilize. So far, I've talked about AIM architecture, which offers high compute throughput at peak. Now let me talk about how to realize such high performance or parallelism offered by the architecture. So we want AIMs to spend most of time in computation, nothing else. So however, AIM is still memory based on DRAM, and thus we still need to activate the precharged DRAM rules prior to accessing DRAM cells. Moreover, in order to put all the banks in compute mode, the command bus may become the bottleneck. So to address these challenges, we end up proposing a few new commands summarized here for compute and command efficiency, making additional specializations in the control path. So among them, like Act 16 highlighted in red here, or all-bank simultaneous activations, or make all-bank, like a all-bank parallel make compute are two most noticeable commands to improve, like a computation efficiency. So now let me switch gears to talk about AIM subsystem. So in this slide, we describe AIM subsystem, a hardware bridge between a host and AIM device. The design goal of this subsystem is to achieve high compute throughput again, but beyond the single device at some scale, and minimize software stack overhead while attaining ease of programming. So this can be seen as the portable reference design that can be deployed in many settings as shown here. For instance, as shown, a host can be AI accelerator, or MPU, or GPU if you wish, or even CPU over PCI interface. For the proof of concept and the performance engineering, we currently implement AIM subsystem on top of FPGA evaluation board with GDDR6 AIM extension card as shown at the bottom. So from the host to the AIM device, there are three main components: the AIM command and data, DMA engine, AIM multicasting interconnect, and AIM controller. So first, we implement AIM controller to generate and schedule low-level AIM command, AIM-specific commands, and typical DRAM commands as well. And we've been focusing on large language models such as GPT again, which requires many channels of AIM devices due to the gigantic capacity. So when dealing with a set of AIM devices, now another key aspect is at system level scalability. So AIM multicasting interconnect here is the key component to enable efficient scaling. They support multiple communication patterns such as unicasting, multicasting, or broadcasting. So among these, broadcasting a command to multiple different channels is quite a common pattern when processing multiple types of large matrix in parallel. So this slide shows AIM control flow from the host to AIM devices. But think about that. So it would be much demanding if a host directly control AIM devices with very low-level AIM command. Therefore, for efficient scalability and ease of programming, so we need to design hardware-software interface very carefully. And to that end, we introduce complex compound instructions to amortize instruction overhead, quite similar to NVIDIA's matrix accumulate instruction. For instance, the instruction shown here, this way, the single instruction denotes a ISR underscore mag or bank, correspond up to as many mag operation as the number of banks times the number of channels times the number of columns per DRAM row, which is quite a lot. Furthermore, this command is broadcast via the multicasting interconnect that I described earlier. So as long as its starting address is actually specified here with the total number of micro command by the software stack, then hardware command generator shown here further decode them down into multiple micro AIM commands as shown at the bottom. In the following sections, my colleague Chanu will talk more about the software stack. Give me a sec, yeah.
Okay. Hello, my name is Chanu, and I'm working for the PIM subject team in SK Hynix. In the previous slide, we talked about our hardware platform. And now I'm going to introduce our soft test tag that runs on with AIM evaluation platform. Okay, this is a motivation. In order to increase the value of new memory solutions such as AIM, expanding the ecosystem is of paramount importance. So to achieve this goal, we have developed an SDK to allow any DNN models to be easily adapted by operator-level APIs. Before introducing our soft-test tag, I will walk you through control sequence for this AI operation with AIM. On this slide, you can see this AI operation for the fully connected layer. And this example is a weight matrix multiplied by vector plus a bias. And so this is an architecture of our GDDR6 AIM, as we mentioned in the previous slide. You can see there are 16 banks here and one global buffer, accumulation registers, and result registers. You can see two types of command. One is AIM host instructions, and they are generated by host processor. And the other type of command is AIM commands that are generated by AIM-DMA and AIM controller. And before executing this MAC operation in AIM, this weight matrix should be stored in DRAM banks, like here. And so to write this weight matrix into DRAM banks, we use normal memory write operation, not AIM command. And this vector should be write in global buffer, and its BIOS data should be stored in BIOS accumulation registers. After that, we can issue MAC command and activation function command. Now we can retrieve the result of this AI operation from these result registers. Since conventional DRAM doesn't have a special way to access this kind of buffer or registers, this AIM command must be used to access them. Okay, in this slide shows how host processors can control AIM, and the main role of our soft-test tag is generating these AIM host instructions efficiently. Okay, now let's see the overall architecture of our soft-test tag. In this slide, this part represents our hardware platform that we mentioned in the previous slide. And our soft-test tag is divided into 4 parts: kernel device drivers, runtime libraries, DIMM learning frameworks, and applications. When it comes to DIMM learning frameworks, our current SDK supports 2 DIMM learning frameworks, PyTorch and Hynix runtime. And this is runtime library, and the main role of this runtime library is memory management, handling of big kernels, and generating ISR instructions. This runtime library exposes a number of OP kernels to user side. So any AI developers, they can easily modify their applications by using these OP kernels. And this module plays a role in the compiler, since this module generates host instructions. This is kernel space, and there are 2 device drivers. One is AIM device drivers, the other is DMA device drivers. With this full soft-test tag, now we can run a number of PyTorch and Hynix runtime applications, such as GPT-2, LSTM, and so on. And the other main feature of this software stack is it supports software emulator, and it emulates the functionality of this hardware. That means with this emulator, we can develop any AI applications or DNA models that can run with AIM without real hardware. In a moment, I will elaborate on this emulator. In this slide, I talked about our software stack, and now let's take a look at each module in detail. This is a minimized diagram of our software stack mentioned in the previous slide. And this slide shows this module, AIM-OP kernel, and our runtime library provides a number of AIM-OP kernels. And this slide shows some of them. As you can see here, our runtime library provides various AIM-OP kernels, such as AIM linear P, AIM sequential P, and so on. So this module in our runtime library exposes these AIM-OP kernels to application side and framework side. So any DNA application developers, they can easily modify their own applications by using these OP kernels. Okay. Let's see the deep learning framework side. The framework in our SDK provides easy programmability for developers. And as I mentioned, our software stack provides two deep learning frameworks. One is PyTorch and Onyx runtime. And this slide shows PyTorch framework. And in order to support these PyTorch frameworks, we have implemented this extension layer based on C++. And to run any PyTorch application, developers can just tweak their own applications. And let's see an example here. This is a PyTorch application, and you can see here the PyTorch LSTM operation here. And if we apply these two AIM utility functions on this model, this model will be converted to AIM operator level API. So therefore, this model will run on the AIM device. Next. Okay, let's see the Onyx runtime applications. To support Onyx runtime framework in our software stack, we have implemented an execution provider layer. And this is an example of Onyx runtime application. So in order to Onyx runtime application on AIM, developers simply add this AIM execution provider into the EP list, and which will make the AIM execution provider the default provider. And some nodes in this Onyx graph will be uploaded to AIM, like this diagram shows. Now let's see the memory allocator in our software stack. Our memory allocator divides into two parts. One is for the host memory, and the other is for the device memory. And the device memory refers to the memory in the FPGA board. So, and it allocates the buffers from the host DRAM and AIM and FPGA internal memory named GPR. And it manages the virtual address of each buffer for each process. And it has a hierarchical architecture as shown in this diagram. And in addition, so since AI operations are performed in AIM, the weight data should be stored in DRAM banks with a specific layout. Since this memory allocator manages this kind of data layout, developers don't need to worry about it as long as they use this kind of memory allocator APIs from our SDK. Okay. This module shows the instruction, ISR instruction generator module, and this module plays a role in the compiler. And I will walk through the process of generating the host instructions and dispatching them to the hardware. You can see this fully connected layer and runtime library divide this way matrix into several tiles. And this runtime library generates ISR command for each tiles like this. And this process is performed only once at application initialization time. And the generated ISR command is dispatched to hardware through the DMA at every inference time like this. Okay, let's see the software emulator more detail. This part represents our hardware platform. And as you can see, our software emulator has several sub-modules. You can see this AIM-DMA model mimics the AIM-DMA engine inside of this FPGA. And the AIM-DMA controller model mimics AIM controller. And the AIM model mimics the functionality of our AIM device. With this software emulator, we can develop any AI applications or DNN models with our real hardware. And the other main function of our software emulator is it supports performance model. That means with this performance model, we can estimate the performance gain with any AI applications. And also we can estimate not only the total execution time of any applications, but also the execution time of each individual host instructions like this. And the other benefit of using the software emulator is the flexibility of the hardware. Since we can easily change the hardware configuration, such as number of channels and operation frequency like that, by simply modifying this configuration file. And this software emulator is very useful to develop any new models with AIM. For instance, when we implement new DNN models with AIM, we also use this software emulator for the sake of convenience, even though we have real hardware. After completing all development with this emulator, this hardware, real hardware, is used for only verification at the end. So far, I have introduced our software stack, and now I'm going to share the performance result that we obtained from our evaluation platform. This slide shows a performance evaluation result on AIM, and we evaluated the performance with the CPU-based system. And we used the workload of GPT-2 and GPT-3 text generation model. Because those are the most popular and memory-intensive workload in the natural language processing field. And on this slide, you can see this architecture that is GPT-2 model. And the GPT model consists of several decoder blocks. And the image on the right represents the one decoder block. And one decoder block consists of a number of layers, such as normalization, fully connected layers, and so on. And the layers in orange will be offloaded to AIM. And there are 4 fully connected layers in this graph, in this diagram, that can be offloaded to AIM. And since AIM can support activation functions, one activation function named GetLoop can be offloaded to AIM as well. As you know, so fully connected layers are the most memory intensive in this architecture. So AIM will be very helpful to reduce memory bottlenecks in this architecture. Now let's see the performance result on GPT-2 XRAG model. And in this graph, x-axis represents the peak bandwidth of each system, and the y-axis represents the execution time in seconds. And there are 3 bars here, and the first bar shows the execution time on CPU-only system, and the second bar shows the measured performance on the evaluation board, and the third bar shows the projected performance. And in the case of the second bar, so since AIM can run at 16 gigabps, but we measure this performance at 2 gigabps because of the I/O speed limitation of the FPGA. And in the case of the third bar, so this is a projected performance at 16 gigabps. We measure this performance by using performance model in our software emulator that I mentioned in the previous slide. And you can see there are 3 colors here. Blue area represents the data movement overhead between CPU and FPGA memory, and the orange area represents the layers that can be afforded to AIM. And the gray area represents the layers that should be performed by CPU, such as nonlinear functions, because some AI functions cannot be supported by AIM. And according to the second, the measured performance, even though it has much lower external memory bandwidth, but it has 2.2 times higher performance than CPU-only system, because it has higher internal bandwidth with bank-level parallelism. And in the case of the last bar, as I mentioned, we assumed that it is running at 16 gigabps. It has higher performance than second bar. Okay, now let's see the result, performance result on GPT-3 13 billion configuration model. GPT-3 model has a larger parameter than GPT-2, and as you can see, GPT-2 XRAG model has 1.5 billion parameters, but GPT-3 13 billion model has 13 billion parameters. That means GPT-3 is more memory intensive than GPT-2. So CPU suffers from more memory bottlenecks on this graph. That's why we can see higher performance gain by using AIM on this graph. In other words, by having a more memory intensive workload, AIM will be more effective. We are now distributing our SDK to academic institutions and industrial companies. So if you would like to conduct research our SDK, please contact us at with this email address. Thank you. I will hand over.
All right, so this brings us to the end of presentation. As I promised, yeah, I also stated all the references here. Some of them are for circuit level, or some of them are architecture, software stack. So please refer to them if you're interested in. We're gonna stop here.
Okay. Well, thank you very much for the great talk. I think you have explained many interesting details about the system. Are there any questions from the audience?
So great talk. What I was missing in the diagram, some of the excellent GPUs, I have no idea how it works internally. Who is responsible for generating the local controls? It's going to be the device and this is stuff like refresh. So when you run your AIM units, you still have to do refresh.
Could you hear the question, Donkey?
Oh, not really at all. Could you? Yeah.
Yeah, I think I can repeat. So the question basically is who is in charge of generating low-level signals? For example, DRAM refresh.
DRAM refresh. Okay. Yeah. So that's a good question. So, this is nothing different from typical DRAM. Refresh command or activation pre-charge are all generated by memory controller for typical DRAM. That's the case here too. AIM controller that includes GDDR6 controller functionality generate all the refresh commands.
Okay. Yeah, thank you very much for the answer.
Sure.
Yes, one more question.
Thank you for the talk, and I have actually two questions. First one is about how much did the chip size increase with the PIM law? So it is a chip size overhead. And second one is that why did you measure CFC at 2 gigabps?
So
can I ask one more? Do you have any result with the GPU baseline?
okay, so the
area overhead and what GDDR6 PIM and GPU based comparison.
So yeah, the first question is what's the area overhead inside the AIM chip due to the execution units?
Okay, so I unfortunately don't remember all the numbers, but we disclosed the area, dedicated to processing unit in our SSS paper or the extended journal paper. So please go look at the papers.
Okay, that sounds good. Maybe for the other two questions, I think it's would you like to come here in case that I don't? Okay. So the second question it was about the how do you measure the results for the 16 gigabit version?
I see.
So I just wonder why.
So it was going to be 16 gigabit, but it's only 2 gigabit, and he wonders why.
I see. So I guess let me also okay. So our current setup is based on FPGA system. So due to limitation of FPGA IOs, we're currently running AIM subsystem at 2 gigabps, as Chanuk said. But GDDR6 can run at 16 gigabps. For this time being, we don't have any ASIC or the system that fully utilize the AIM subsystem. So the way we estimate the performance is based on our performance model. So we have very precise cycle level accurate performance model that is validated to the measurement from the FPGA system. With the model, we are able to scale the estimated performance if we run at 16 gigabps. Hope I answered the question.
Yeah, I think so. Thank you. And the third question was about the GPU baseline, right? So how did you measure the performance of the GPU baseline?
Give me a sec. Did you have a GPU result or? Okay, so I don't think we presented any GPU baseline result. Actually, we are doing so. We are collecting a bunch of performance data from GPU, CPU, and the other accelerators, but I don't think we actually presented it this way. But yeah.
Okay. Okay, sounds good. Thank you very much. Are there any other questions from the audience? Okay, so then it seems there are no more questions from the audience. So yeah, I really appreciate your time. Yes, so the very interesting talk. And yeah, thank you. Thank you very much again.
Thank you again. We're dropping out now. Bye.
Okay. Yeah. Thanks everyone for staying here until the end of this tutorial on processing in memory systems. I just want to wrap up by showing just a couple of slides about our let's say the optional part that unfortunately we don't have time to cover in this tutorial, but I think it's good that everyone has the opportunity to try by themselves. Here in our website, you can find everything, all the materials that we have shown today, and even more than what we had time to show. The very last thing is just the optional part, as I said, because there is no time during the duration of the tutorial. But this is the hands-on lab that you can try by yourselves. There is a presentation here with some instructions. Doesn't seem to come, which is not good. But anyway, there is one presentation here with instructions about how to access the UPMEM-PIM system, a real UPMEM server. This is going to be available until 6 a.m. today or tomorrow, if I'm not wrong. And I don't know why this doesn't show up. Let me see if I can download maybe.
You successfully SSH into the UPMEM server?
I didn't try today, but it should work. Anyway, did you check the instructions in the? Yeah. I can take a look with you maybe if.
I was trying to do this Python, but I don't have access to Linux.
Yeah, let me just 1 second share this. Okay, so let's pause this. Okay, so this is the handout of the hands-on lab. As you see, it has a lot of instructions and indications on how to access the server. Is the very first task. That's task 0 of this lab. Accessing the server, you need to configure your SSH config file with this information here. You also have to download from the website. There is a link here to download this key, the private key that you need to access the server. I mean, it's a zip, but you need to unzip first and place it in the corresponding folder .ssh in your machine. And after that, as you see, there are also like some tips, etc. And after that, here in section 3, you can start the actual work. First thing is transferring data between the main memory and the PIM-enabled memory, the different types of data transfers that we presented and discussed today. And then the remaining tasks like this, for example, task 4 is about implementing your own code for as a DPU, basically writing the code for the tasklets. And then here the task suggests to try different things, like for example, different sizes of data transfers between MRAM and WRAM, and also generating results for different data types like char, short, int, float, double, etc. This way, you are going to see the performance difference. Basically, it's kind of reproducing, in some sense, the results that we already generated in our work. There is much more here for different operations as well. There is a task this task 4 is a vector reduction, implementing a vector reduction with, in different ways. It can be implemented using mutexes or barriers or handshakes. And each of them will have different performance depending on what's the overhead of the synchronization. And finally, there is a bonus task only for the very good students. In this case is implementing RGB to grayscale conversion. The handout proposes 3 different methods. And I think it's interesting to try because there is also, like different potential optimizations that you can try, like even like, for example, using lookup tables to perform this transformation, as you can imagine, because this is a system that is memory rich, let's say, you can make use of all that memory to place there some lookup tables that will likely be faster than computing on the WIMP cores. And I think that's also something that we will probably discuss in future lectures and in future editions of this tutorial as well, different ways of optimizing code and making it more efficient and deal with the fact that you cannot have a powerful CPU, but you can enjoy much higher memory bandwidth and much shorter latency of access. There are, the last thing I wanted to say that here you also have a link to the template that is also in the website, and I think it's pretty convenient for you to start. You don't need to write code, all the code from scratch, just the important parts, because in the end, most of the times you can reuse code for loading or allocating a DPU set or transfers, etc. So that's basically it. Today you have access to the server, as I said, until 6 a.m. But if after that you want to continue working and trying different things, you can also use the Docker file. Well, you can either install the SDK, the UPMEM SDK in your server and use the functional simulator. And if that causes any issues in your machine, you can directly use the Docker file that we provide as well in the same template.zip file. So yeah, I guess that's all from my side. I think, well, I hope you guys enjoyed the tutorial. My impression is that it went well. We would have liked to cover many more materials, but we don't have an entire week. So yeah, so hopefully if you are interested, you will check all the materials that we have in our website or course website, and many more talks about our processing in memory works that you can find in our YouTube channel and in Professor Mutlu's website. This tutorial will hopefully be delivered again in ISCA 2023. I think it's on July 18th, on Sunday as well. So I hope to see you all there as well, and hopefully we will have for sure new materials and hopefully some interesting invited speakers as well, invited lectures. So thank you very much, everyone.